Why are we having trouble? This is a preview? Whoop. Are we going? Are we live again? I'm trying to see, or if my stream failed and for some reason I'm having trouble today. Not working for me. We'll try reloading. Let's see. It says it's live. Anyone see me yet? I'm hoping we're back. I am not exactly sure if we are back. It looks like it's broadcasting live, and if so, then I'm going to shut the door. Does everybody see me? Oh, there you are again. Okay, so we're back. Good. I'm not exactly sure what happened. It just kind of failed in the middle of everything. So I have the door open to my studio right now, and I don't know if that's going to be distracting. So let me know if you guys hear stuff through this microphone, because this isn't a house, so it's a very busy house. And so if you hear stuff and it's too distracting, let me know. But I have the door open just in case there's something going on with the connectivity, because I have a few wireless devices. So everything looks good right now. You can hear me loud and clear, and you can see me perfectly. Okay, so we'll start with that. And to begin, I will stop periodically to check out what's going on here. I probably will minimize this in just a minute so you don't get too distracted. I know it can be very nerve-wracking to watch endless replays of me going on and on and on down the screens. I apologize for that. I just wanted to make sure I'm seeing your feedback here so I can be sure to get everything working properly. And what I will do, and it looks like I need to adjust my camera just a tiny bit to pull this up a little bit. Unfortunately, things always seem to get cropped sometimes. So let me fix that. Hopefully that fixes it. And hopefully you all can see the entire screen now, that it's a live Q&A mini course all about indices. And I'll make sure that it comes up on the feed properly. For those of you who do not know me, while it's doing that, my name is Dr. Tamitha Scove, and I am a space plasma physicist, which sounds kind of scary, but basically what it means is that I can bring you the space weather just like a regular meteorologist brings you the terrestrial weather. And I've been doing this for quite some time now, and I'm really enjoying being able to educate everybody with these mini courses. There's a lot of misinformation out on the web, and a lot of people who are struggling to try to understand it, and then when they think they've understand it, they go out and they explain it to others, and unfortunately that just passes misinformation on. So I'm doing my best to try to help everyone get a better handle on some things that are a bit tough. I know indices has been something that a lot of people have asked me to do for months. I know people live and breathe by some of these indexes that we use in space weather, but unfortunately they're designed mainly for scientists, so they've not really been made publicly friendly. And although all that data is out there for you to peruse, the problem is if you don't understand what you're looking at or why you're looking at it, then it can be very frustrating, because space weather is fickle, and it does certain things at certain times and not things at other times. And so one index may be going crazy and another index is kind of flatlined. And if you're looking at the wrong index, you think, well, space weather's not doing anything, or wow, space weather's crazy, and really neither and both are the correct answer. And so I'm going to try to help you today, although indices are not necessarily anyone's favorite topic. I mean, they're just a bunch of numbers people throw together, and who wants to really look at that? But they really do relate to some cool stuff, and they're part and parcel of how us scientists try to organize some of the information that we get in bite-sized chunks, so that we can quickly go back and reference something and understand maybe the physical process behind it, or at least understand how certain processes work together by seeing when something is really disturbed just at a quick look glance, and say, okay, now I need to dive back into this in more detail. And I saw that this index went nuts when this one did, or this one went first and then that one. There's all these little things that we pay attention to So we've derived these indices for these reasons. And I'm sure by the end of this, you will still be scratching your head about a few things. Join the club, because not everything is known about space weather and about how the ballet, the beautiful ballet within our own magnetic shield works. And we are deriving new indices all the time. So if it feels like we're kind of just scratching the surface of understanding how a lot of different complex issues function up in the Earth's magnetic shield and down even into the Earth's atmosphere, you are absolutely correct. We really are. And I think this will kind of set the stage for understanding that and getting excited about what comes next. And believe it or not, the Mars InSight lander is part of that. So let me just make sure. I'm going to check this feed one more time to see if anybody is worried or having problems getting to me. Oh, that's sweet, guys. So much better than fear-mongering. Yeah, we can't fear-monger because we got to try to make this part of our world, right? If we don't understand space weather, and if we just scare the daylights out of everybody, they're just going to switch off. And if all the blockbusters in Hollywood, that's what they do, is they scare the poop out of everybody with these Armageddon kind of scenarios. And yeah, those scenarios exist, but that's not what you can live with. I mean, it's kind of silly to even ponder those or even talk about them, when in actuality, you're probably going to live your entire lifetime not seeing one of them, but you're going to see a lot of other stuff that is a real pain in the tush that you've got to just deal with, and that's kind of the same thing with terrestrial weather. All of us can think of, a caldera exploding with this huge volcano that's going to wipe out all mankind, and a winter that's never going to end, or a super storm that's going to be a huge hurricane that covers half of North America, or whatever. We can all envision those scenarios, but it's not really productive to talk about them. It's a lot better to talk about rainstorms and storms that we can do something about, and live through, because that's what we're going to be seeing on a day-to-day basis. So, okay. Tam, you're 59. Sorry, I don't know that. I'm sure that's 5x9. Right, thank you. I'm so glad, thank you. Took me a second. Okay, good. So everybody is happy there, so I'm going to close this down and start talking about some indices. Let me... I'll just go back here, so I'm on my Patreon feed, so if people start asking questions there, I can also talk to them. Now, what we've got here, these are the people that I'm bowing to every single day. You are my patrons who are supporting me. All of these people have supported me at the mini tier level, the mini course level or above, and I can't thank you enough. You guys keep coming up with amazing dialogues. I've already got like 4 or 5 mini courses kind of thought up in my head simply because of things that you guys have asked me to do. And the next one may end up being one about where I dissect. I actually take piece by piece one of my forecasts, or maybe several of them, maybe during solar minimum and solar maximum or something. So that's kind of the dialogue going on for maybe even the next month. And the history of space weather, that's another really cool one. Something about Mars InSight in a much more intense way, or Parker Solar Probe. I mean, we're just having these wonderful dialogues, and I cannot thank you all enough. Had a wonderful VIP session just yesterday with most of the members of the VIP steering committee, and I just love the direction we're going. So many intelligent people. I mean, I bow to you all of you guys that want to know space weather and engage me in dialogues and come to Patreon and do all of this stuff. You just overwhelm me. You are so brilliant, and you ask such insightful questions. And it's so obvious that you want to know what this weather is, and you want to make it part of your world. And it just tickles me to death that I get to be so intrigued by you, and even in your life stories. I get to be so intrigued by what you do, and I just feel so blessed that you are all with me. So thank you very much. And with that done, let's jump into this. Now, there's going to be a lot of text in this particular session, so I do apologize for that. Some of it may be too small to read. If it is, I will probably be reading over it anyway, and it'll start the dialogue. But the nice thing is that almost all of this stuff And a lot more information will be found at the ISGI website. Here it is here. This is the one that just talks about geomagnetic indices. This is a fantastic site for all the indices I'm going to talk about and a few more. It goes into much more detail, and then it links to yet another site in Potsdam that I will talk about a little bit later that goes all into Bartels and how he created KP, because that's the basis for a lot of these different indices. And as you'll see, this is not a trivial thing to create these indexes. And really, how it kind of started is that we wanted to understand a little bit more about what was going on inside the Earth's magnetic shield. Believe it or not, there are a lot of different current systems, and some of you guys know this. There are current systems that are on the outside of Earth's magnetic shield. There are current systems that are down the tail of Earth's magnetic shield, and I'll go into those more in a second. But there's just a ton of them. And through something that we call magnetic mapping, and I'll talk about that in a minute too, we can actually begin to understand these current systems and to some degree isolate them, or at least minimize the contribution of one current system to understanding what one current system is doing and disturbing the Earth's shield relative to another. And it's simply based on where you are on the globe, your latitude and your longitude, your magnetic local time, as we call it. And by being savvy about where we place stations, we can actually ferret out what these different, to a great degree, what these different current systems are doing. So to introduce it, what we're going to talk about when we talk about these currents that are flowing inside the Earth's magnetic shield and down into the upper atmosphere, which we're calling the ionosphere for all you amateur radio operators and scientists who might be watching. Yes, I do use these two terms synonymously. This is obviously the scientific term, but the ionosphere, but it's oftentimes a little jargony. So I will just say upper atmosphere, and it just means way up. where molecules don't even hit each other anymore. But at any rate, all of these currents that kind of swirl around up in there, they will actually induce magnetic field changes, variations, disturbances on the ground. You can read them with a compass. You can read them with a magnetometer. People read them with their cell phones all the time now. There's all sorts of little apps that you can use to read magnetometer readings. Not very accurate. I wouldn't trust it, but nonetheless. These variations are typically separated into quiet systems and disturbed systems. So when the space weather is extremely quiet, like it was maybe a day ago or 2 days ago, you would see a lot of this type of variation, very smooth variations. But the disturbed systems, these are the things that bring us to the types of indices that we like to look at. And these are the types of indices that we use all the time. KP, for example, or even local K, which I'll talk about. The A index, right? The little a index, the big A index, the double A index, the AM index. I mean, there's so many. There's a CP index and a C9 index and a C48 and a C24. I mean, it's just you can you can get overwhelmed very quickly. But they are all based on the KP system, which is from a disturbed current systems. Okay, and here's, for example, a quiet system. We call it SQ, solar quiet. This results mainly from sunlight, from kind of a thermal heating of the upper atmosphere. It also has to do with the magnetic field. I'm not going to go into the details, the physics of how it was developed. That's beyond this, the scope of this talk, because I've got to stay focused on indices. But there is a lot of physics involved in how this current system came about and why it's so steady. But it results principally from the currents flowing in the E layer of the ionosphere. Those of you who know, the E layer is where you start really getting good charge distribution, a lot of good conductivity in the E layer. Disturbed variations, which are down here, are comprised of several different current systems, and you can see them in color here. Don't worry, I'll blow this image up in just a moment, so you get to see it better and read it. Yeah, okay, and they're within both the magnetic shield, which like I said, I'll blow this up in a second, but they also penetrate into the upper atmosphere. Now, these indices have been derived, and we call them geomagnetic indices. They've been derived in an attempt to isolate the magnetic variations that are been associated with these different current systems, and oftentimes it gives us a lot of information about what's going on with these different things and in different regions. And they drive different physical processes inside Earth's shield that then cause other processes to happen. And that's when we get into really cool stuff like MMS and reconnection and all these other really cool things that happen in this very complicated ballet. So like I said, here's the link to the ISGI site. And I will put this in the description, at least on Patreon, if I don't remember to put it in the YouTube. Now the Patreon post that is associated with this is open to everyone, so you guys can, no matter who you are, you can get access to anything I put in there about this mini course. Okay, so solar quiet, we call this SQ. Anybody ever heard of it before? Probably not. We don't really talk about it all that much. It's kind of washed over because good old Bartels managed it back in 1949, kind of got rid of it for us. This is it deals with low to mid latitudes, and it's always during quiet times that we can really see this, and I'll show you an example in a moment. Mostly this is shielded from the effects of magnetospheric current systems. It's mainly affected by this thermal input, this what we call the ionospheric wind dynamo. And it's on the front side, as you can hear. Here's a picture of the side of the Earth, so you can see the dark, that's the nighttime. Here's the daytime. You can see the equator essentially right here, and you have a current system that is circulating. And then in the opposite hemisphere, it's circulating the other way, okay? So thermospheric nuclear winds are driven by solar heating, and these currents occur between 90 and 200 kilometers, so definitely up in the E layer and even above. The ionospheric dynamo depends upon the conductance and therefore on the solar cycle, so it does change and it does vary. It varies seasonally. It varies with the solar cycle, obviously. And obviously, it also varies with the local time because you don't have the currents on the night. It has to be sunlit. So depending upon where you are on the globe, what is your local time, you will see a different part of this current system, okay? And here's a link if you want to get that image or read more about it. So that is the SQ current system. It's going on essentially all the time. And I'll talk about that. That's one of the main quiet systems. There's another one called the L system, the L variation, and that's a lunar variation. So we have a solar variation and a lunar variation. And I'll talk about the lunar variation in a second, but only as like an example, because I will show examples of these. Now, for the disturbed stuff, and this is where things get fun. Here is a picture of, and this is a very famous picture. We got a lot of people who have put this in their papers. So I hate to say this, but I forget who first put this out. But this was something this is a picture that I saw when I was a grad student, and that was 100 years ago. So that lets you know how old this picture is. And it's been reused many, many times. So what you're looking at is a cut of the Earth. So this big bubble, this big bubble is the Earth's magnetic shield. And the sun is on this side, the solar wind blowing against it, boom, here. And it blows and it pulls the magnetic tail all the way out like that, like a comet. I don't know why I'm going brrr today. Please forgive me. So what you're looking at here is kind of like a cutout of the Earth. It's this part here, this plane has been cut vertically. This plane has been cut horizontally. So if you took an apple and you went cut like this and then cut like that and took out a quarter of it, that's what you're looking at. So that's why the Earth looks so funny. So what they want to show you here is what it looks like in the vertical plane. And you're seeing magnetic field lines this way. This is the front part of the magnetic field, and then the back part pulls out as a comet. Here is what we call the cusp region, where stuff comes in. And then here is the equatorial region. So this is the flat region, right at the equator, essentially. And so you're seeing other things going on in this area. Now, Earth's magnetic radiation belts, Earth's magnetic field, of course, is a toroid, and I wish I had my slinky with me. I don't see it right now, or otherwise I would put it up. So yeah, I could show you the toroid. Here is part of the toroid that comes out, and it comes out like this and goes back in. So the slinky is kind of like this, okay, the coils. And inside this region in here, circling the Earth, are the radiation belts. But we also have something called the ring current. They are basically co-located. The ring current and the radiation belts are co-located. The difference between, and everybody knows the radiation belts, but very few people know the ring current. The reason for that is the radiation belts take out spacecraft. They've got very energetic particles, and they can really damage things and damage astronauts. However, the ring current is much lower energy. So it's the same kind of thing, the same kind of processes guide them, and they go in the same areas, but the ring current is low energy stuff where the radiation belts are much higher energy stuff. But this ring current becomes very important, and we'll talk more about that in a little bit. We also have the magnetopause current. This is the current that what happens when the solar wind hits the front of the Earth's shield. There are currents that develop. You've got magnetic fields that are changing and moving. You've got to equalize the pressure against here, and believe it or not, the magnetopause current actually helps equalize the pressure as the solar wind comes in. And so that is very much a function of the strength of the solar wind as it comes in. You also have the tail current. That's part of where the magnetopause current closes, along with some of these others, and I'll show you in a minute. I don't want to get too complicated. We have cross-tail current, the current sheet in here, and we also have field-aligned currents. Now, the field-aligned currents are the ones that create aurora, that help create aurora. We also have a partial ring current that connects these things, and I'll show you a more complicated picture in just a second. But as you can tell, there's a lot of stuff going on, right? And all this stuff gets jacked up and excited and stronger when we have solar storms. As a matter of fact, one of the things where people have asked me in the past, well, we don't really have a strong BZ component, southward BZ component, which is usually what you look for a big magnetic storm. But we have but they're saying, but I'm seeing aurora and I'm seeing, activity. Why is that? And what I do is I go look at the BY component. This is the component that goes this way. And if I see a big component like that, then I know this component, this current is big and this current is big. And when you have big, especially big cross-tail currents, you can once again get the magic that happens in the tail that sends and slingshots particles up into the aurora zones. So you don't always just have to look for a big BZ component southward. You can also look for a big BY, because that's what helped drive some of these currents here. So it's again, it's a complicated ballet, but these current systems really are what are some of the main drivers of the effects at Earth. And so we'll talk more about this. Now that we know we have these currents, how do we begin to isolate them in indices, or how do we isolate them at all? We may have a current that's strong out somewhere, let's say down the tail, very far away from Earth. But how do we know where to measure it? How do we know which wiggle of the magnetic field at Earth is going to correspond to that particular current? Or if we have the ring current getting all excited, well, how do you isolate that? Without having a satellite up in space, how do you determine, just by looking at the wiggles of the magnetic field on the ground in ground magnetometers, how in the world could you possibly know what's going on up there? Well, it's the magic of mapping the magnetic field. This is one of the coolest parts of what I consider to be magnetospheric physics, is that the Earth's magnetic shield, because it's magnetic, these field lines are not allowed to touch each other. They can't. It's just the rules. Look, talk to Maxwell. I didn't make the rules, he did. And Maxwell's laws they define how magnetic fields work. And one of the rules is that magnetic field lines do not touch. If they do, then there's issues. We call that divergenceless field. And, well, that's one of the things how we define it. There's several other ways we can discuss it too, but that's just one. But looking at it from that point of view, one of the unique aspects of Earth's magnetic field is, and this is a simple drawing of it. As you can see, here's Earth here, here's the North Pole. It's slightly off from the geographic pole, but that's not really important here. It's a simple drawing. I know it's not perfect. It definitely doesn't show the influence of the solar wind. This is just a dipole magnetic field. But it's very instructive in this point of view. And the reason why I say that is, if you notice, down here, let's say we're going to take this line here at the very closest part of Earth. Notice that the lines come out of Earth really low latitudes, right? I mean, relatively speaking, not up here, but down here closer to the equator. And it goes out and then comes back in. At a southern latitude, that's pretty low, and it goes up past the equator and back into Earth at a higher latitude, at a northern latitude, but still low. kind of the conjugate. And then you go a little bit further out, and you have another magnetic field line. Now remember, they can't touch, so they've got to be drawn outside. This further line has to be drawn outside of this one. So it starts at a higher latitude, higher southern latitude, goes out up past the equator area and back in, and it also penetrates in the north at a higher latitude. And again, the next line that goes out even further away from Earth has to go to an even higher latitude. See that? Out up to the equator and back in at an even higher latitude. And we keep doing it, and we keep doing it, and we keep doing it. So the further you go out from Earth, and you look at what the magnetic field is doing out here, the higher latitude it maps to. And what that means is if I take this magnetic field line way out here and I wiggle, right? I do something, I'm mad, I want this thing to shake. So I shake the poop out of this thing. Well, those wiggles go, and they wiggle up here. And so if I'm a person standing on the Earth up here at the North Pole and I look at my magnetometer and I go, oh my gosh, well, I know that somebody's wiggling it, but they're not here. They're way out here. So so this is something that's happening very, very far away from Earth. And that should cue you in immediately that, wait a minute, if we can stand at different places on the Earth and see what's happening at further and further locations away, then how does that work for the current systems, right? Look at the ring current, for example. Ring current's close. Here's the closest, this brown one. This is the ring current. Okay, here's Earth again. Okay, here's an equatorial plane. So we're kind of looking down. Our view is kind of looking down a little bit at Earth. Here's the equator, dot, 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 that little black line. And here's the ring current out here, but it's the closest current you see, right? So what did we say? Close. Close to Earth. Where is that going to map? Low latitude. Okay, well, what's further out there? Well, the next one is kind of like, let's say, a partial ring current. Let's not do the boundary layer. So let's do the partial ring current. Let's do blue. Okay, I'm skipping the green one because the green one's a little bit more, it's field-aligned currents, but they're mapping out here. So you have field-aligned currents that map in here and also the partial, between that and between the partial ring current. So we can do green, blue, or the green and blue lines. So they're further out from the ring current, right? They're getting from mid-latitudes up to high latitudes. Well, I'll say that in a second. And the reason why I say that is because if they're outside of this, just outside this line, well, then they got to be this line, right? And as a matter of fact, we'll just say it's the whole region in here. And where does that map? Oh, a little bit higher up, mid-latitudes. And where does this one that's further out map? Oh, even further out. Oh, well, we're getting to high latitudes now, right? We're getting up in here. But the ring current stuff and the region 1, region 2 currents, guess what these are? These are, or not the ring current, sorry, the partial ring current, that's the blue one that comes up. See how it goes up and down into the upper part of the Earth? Those are the field-aligned currents that go in and cause aurora. These are near what we call the electrojets. And that's higher latitude. So you can think, okay, well, if I just watch stations down at low latitudes, then maybe I can just get the ring current. And if I watch latitudes a little bit higher, well, maybe I'll still get a little bit of the ring current, but I'll get more of the stuff that's going on, like aurora. And, well, let's say I just want to get the really high latitude stuff. I just want to get the region 1 or region 2 currents up here by themselves. I don't really want to get any influence from the ring current. Well, let's just do high latitude. Let's not even try to do mid-latitude. And then maybe we can see what's going on there. And so you can continue to map. And then if you just want tail, now this is out in the tail. Now you have a substorm current wedge. Now you're getting substorms. And this is where you get reconnection, is out in the Earth's magnetic tail. But look how far out this red current is from everything else. Now you're talking really high latitudes. Now you're talking the best stuff that's way up high. That's where you can really see stuff, and you're completely or almost completely isolated from what's going on down here. What's going on in the radiation belt zone, in the ring current area, where the big, huge reconfiguration happen for big geomagnetic storms. You can see little tiny things. So like when the tail slingshots little blobs towards you. you actually can read that because you're out here, you're actually mapping up here, and you're completely isolated from down here, and vice versa. If you just wanted to look at ring current stuff, which takes a lot of energy, it takes a big storm to really kind of mess with a system that's as massive as what, essentially are like the radiation belts. I mean, that's a core concept that's always there, a core system that's always there with the Earth. You really have to have a big storm to mess with this. But having a little slingshot, little pea shooter down the tail, shooting little blobs of plasma, little blobs of little sets of particles at you, you don't have to have much energy for that. Matter of fact, that kind of stuff can happen even without solar input. You can have reconfigurations that you can't even figure out what in the solar wind could have triggered it. And that's what happens out here. But in order to see this substorm current and the current wedge and all this and the effects of that at Earth, you got to be at really high latitudes. Right, so up in here. So that is the beauty about magnetic mapping. So if you place magnetometers all over the globe and you organize them properly, you have a ghost of a chance of understanding and isolating all of these different types of things. Is that cool? I've always found that cool. To me, that's the coolest thing about this kind of physics. Anyway, I'm wondering if I should stop and ask if anyone has questions, because that's a kind of the part of the core concept of this, and I worry that it's too complicated. Let's see. So it's unbelievably beautiful how all this science talk is sexy. Thank you. Oh, I love that. It isn't to me too. It's so sexy, isn't it? It's fun. Does that mean does it move longer to the daylight hours you get? Does that mean it does more the longer into the daylight hours you get? Oh, you're probably talking about the SQ variation? Well, yeah. I mean, the more you're in daylight, you're going to be going through a larger part of that current system. So yes, when the Earth is tilted in such a way that at your latitude, your day is shorter, well, then you're going through a smaller portion of that. You're not going through the largest part of that oval of, let's say, one of the hemispheres of the current system. You're going through a smaller part of it, so it doesn't last as long, right? So yes, it really is a geometric thing, and if you map yourself to your latitude, you can see what part of that current system you're going through. And if your day is longer, well, you're definitely going to be going through a larger part of that current system, and possibly stronger too. Oh, Zombie, what a troll. I love him. He's so fun. I hope you stay with us, Zombie. I just absolutely love it. I'll let everybody else tear you apart, but you are fun. Okay, let's see. We are in Sacramento. Is that considered mid-latitude or high? That's definitely mid-latitudes. Although I will tell you, in 2015, we had aurora as far south as San Jose 3 times that year. 3 times. So, there's definitely going to be some changes when it comes to where aurora reporting is going to be and what is considered part of the auroral zone. If we can get during a very weak solar cycle and during only a moderate storm, we can get aurora south of San Jose, south of Sacramento, essentially. That's pretty cool. We obviously have been wrong about a lot of things. But I will talk a little bit about how things are changing, so that makes a difference too. Okay, let's see. Oh, good. I'm so glad. What is the difference between heliophysics and space weather? That's an excellent question. I'll answer that really quickly, and then I'll jump back, because it looks like everything is good. Wait. I have to respond to Zombie. I said lies because you said you went to school 100 years ago. Your cellular structure doesn't look a day over 35. Thank you so much. I am much older than 35. Anybody who's seen me in person knows I am definitely not 35. I have a 9-year-old daughter, so that tells you something. And gosh, anymore, just Google me. I mean, there's so much information out there. I couldn't hide my age if I wanted to. The days of that are over. So I am older. I appreciate the compliment, but I am much older than 35. Okay, so the one question was about heliophysics and space weather. So yes, space weather is a subset of heliophysics. It's probably the most well, let me use the word that you guys have already used. It's probably one of the most sexy aspects of heliophysics. But heliophysics basically is the physics of anything that is in the heliosphere. So our sun, just like our Earth, has its own magnetic shield, and the solar system is inside that shield. As a matter of fact, the Voyager spacecraft are just beginning to try to cross that and get out past that shield. So anything inside that shield is heliophysics, believe it or not, even planetary physics. So so a heliophysicist will study aspects, let's say flux ropes on Mars, which does happen. We have what we call flux transfer events in the Martian ionosphere. I'm sure that sounds like Swahili to you, but that is heliophysics. Is it space weather? No, not really. But there are space weather implications of it because Mars doesn't have its own intrinsic field, so it doesn't have a very good magnetic shield of its own, which is what's going to kill colonists later, but that's another story. So the space weather of Mars is very much connected to the upper atmosphere of Mars and some of the ionospheric events that are happening, and the fact that the sun is ripping the atmosphere off of Mars constantly because it's not being protected very well by any type of magnetic shield. But there are all these different questions that we want to have answered in heliophysics that really can forward the science and forward the science of space weather, but they're not necessarily and technically space weather. And of course, there are two sides to space weather. One is the research side, which I've been involved in since I was a grad student, and then there's this operational side, which has been given over to NOAA, but really I'm trying to create a broadcast and an operational side for the public. And that's really part of what all of this is about. So this operational side of space weather, I wouldn't even know if that would be classified as heliophysics research or heliophysics anymore at all. It may eventually be called weather, maybe just part of meteorology. And we are in the process of inventing a new field called space meteorology. So whether that actually stays as part of the heliophysics division, let's say, of NASA or anywhere else, any other university or department that you want to talk about, I don't know. I really don't know. I think we'll have to wait and see. But hopefully that separates things a bit. So yeah, if I wanted to look at the Io plasma torus, around Jupiter because of the volcanic activity on Io, and it creates this nasty dust ring around Jupiter, that is heliophysics, sure, but it's not space weather necessarily. Not unless we decide to go and try to figure out how to live there. We kind of have to twist it around to understand or try to figure out, well, what concept, what part of that is really space weather and what isn't. I think we can actually define it however we want. I mean, some people might actually call that space weather, I don't know. So hopefully that answers the question. Okay, so do you think the dust storms on Mars could have an electrostatic causal component and not be the result of simply wind? Oh gosh, that's such a complicated question. I will do later a mini course on Mars and Mars Insight, Mars Curiosity, and Martian colonists, and we will talk more about that. But that is so off topic, I won't even start. But that's a great question. So I'm glad we have the chat here I can come back and look at. All right, so it looks like everybody seems to understand the concept of magnetic mapping, and so I'll move on to some of the bookkeeping stuff that I just want to make sure you guys know, so that when you look at magnetometer data directly, you don't scratch your head and go, what am I staring at? Now, just like on the anywhere else, a compass, that will read essentially, well, I don't want to say that. Let me try it a different way. When you look at any type of solar wind data, you oftentimes see, three components, right? You have a vertical component and then two horizontal components, and that unambiguously can label what you're looking at, what the intensity of something is that you're looking at, because you need three dimensions. And that's exactly what we're talking about here. This is a particular coordinate system that has been adopted by magnetometer, ground magnetometer people to be able to understand and systematically coordinate what magnetometers are measuring And although people are used to coordinate systems like X, Y, and Z, they may not be used to H, F, and was still called Z. But there is a relationship between them, and really, I've got two different ways of looking at the same thing. And really, let's start with Z. With Z, oftentimes Z is called, this is straight down into the Earth, often called the nadir direction or the zenith direction, whichever you're looking at. This is why I put both of them. And then you've got the X component. That will always be pointing northward wherever you are, and it's given an X direction. And then Y is always pointed east. Okay, and you don't see here, there you see Y as being eastward. Now that is how you establish the XYZ direction. So if you see magnetometer readings on the ground that are labeled XYZ, you know what directions they point, okay? Now, let's say that we add an actual magnetic field, okay? Let's add this arrow here, this what we call the vector. This is just a direction. It's got a length that is what we call magnitude, that's the strength of it, and then which direction it's pointing, it gives you its direction. That's why what's the definition of a vector. So it basically allows scientists to, and mathematicians to define very specifically everything they need to know about what the magnetic field is doing at a particular point. So that's what this line is. But a lot of times this field vector is not really pointing the direction we want it to. We want to understand what its northward component is, what its downward component is, and what its eastward component is. And so we define all sorts of ways of trying to figure out how to organize it, how to break this thing down into something that lines up with these coordinates, these X, Y, and Z that we like. And oftentimes we do it with what we call a D, the declination angle, and the I, the inclination angle. These are just simply angles, and I'm not going to go into it too much. But if you see a D and an I, basically you're just looking at angles that basically relate the field direction to the coordinate system we're used to this standardized coordinate system, okay? And you see, again, here's another picture. If you don't like that picture, you can see here, this is in that horizontal plane, and you get an angle D and an inclination as it points down. You get an inclination angle, that's I. And so you're able to map, using this idea, you're able to map part of this field vector onto these coordinates that you know better. And then one of the things that we like to get that's really important to us is not necessarily just the northward component or just the eastward component, but it's something that lies in this plane, and that's why they built this little slab here. They're trying to emphasize this. What we really, really care about most of the time, especially for KP and all the indices derived from it, is the H component. Okay, now the H component is simply the horizontal component. So if you take this magnetic field vector and you break it down and using mostly the inclination angle, you want to get back how much of that field is pointing horizontal to the ground. Okay, so if the ground is here, you want to know how much of that field disturbance, that wiggle or whatever, is pointing this way or this way or this way or this way, somewhere in this plane, on this slab. And they say the same thing here. That's what this top part is. So this is the horizontal component, and it's oftentimes adding the X and the Y together. So if you see magnetometer readings in X, Y, and Z, to get the H component, you would add your X and your Y. Okay? Now I've had people ask me that, not very often, but I have had people ask me, how do you get an H component? I don't understand. Mine's an X, Y, Z. How do you get an H and a Z from an X and a Y and a Z? And that's how you do it. You add, and this is the reason why, is because what you want to get is that perturbation, that change, that variation that's in a horizontal to the ground, parallel to the ground, because that's the most important. Okay? So oftentimes, I think I've covered all this, you will see these elements, H, D, and Z. So you'll see the horizontal component and then a declination angle, because that will then allow you to back out Y if you want it. You'll see F, I, and D, so you'll get the actual field vector, the strength and direction of the magnetic field, and then you'll get the two angles, and that will be, once again, it'll allow you to back out X, Y, and Z, or you'll just get X, Y, and Z, and then you have to deal with that. then you can construct the others from it. So that's the bookkeeping part. I know it's a pain in the butt a little bit, but you can always go back and refer to this. These are easy to find. Kyoto is a great resource, and again, I'll put a link to Kyoto, the website. I think they have this figure, if I recall. They have this figure, and they go over stuff like that. But you can also find these types of stuff everywhere. But these are the types of things that you'll be seeing most often, and this is what they refer to. And they really are just different ways of talking about everything, or the magnetic field. If you take one thing away, take away the H component. That it's the component that's horizontal to the ground. It's parallel to the ground, because that's the most important part. Now, moving on to main current systems. So let's kind of review just a little bit. We have a low latitude quiet system. That's what we call the ionospheric wind dynamo. It's this solar quiet variation, right? It's wiggles about, it's about 10 of nanotesla. So about what the solar wind is on any given day. The solar wind is about 5 to 10 nanotesla, give or take. Really quiet, it gets down to a couple nanotesla. But so as you can see, it's really something that is on the kin and on the scale of a quiet day. It's a smooth variation, and along with the L variation, it's subtracted before deriving Kp. And that's what gets tricky. I'm going to go into that a little bit, but not too much. But it's imperative that you subtract this system before you try to do anything with magnetometer data and compare it to any K indices at all. Otherwise, you're going to get it very wrong. And when you see these if you have a pocket magnetometer, or if you have a magnetometer station, there are ways to turn your station into a K reading station, what we call standardized K. You can do this, but there are indices and lookup tables and all sorts of things that you have to take into consideration to do it. So anybody who wants to go out and get a magnetometer and stick it on their, on some weather station, I absolutely applaud you for doing that and wanting to do that. But just know you're not going to get K readings right away from it. And when you look at straight magnetometer data, they most likely have not taken this stuff out, unless otherwise said. So you will see variations that don't necessarily mean that there's some solar storm going on. But these are typically smooth and slow, okay? Now, the next system is low latitude disturbed system. We're going to talk about the ring current a little bit. That is measured by the DST index, and we'll talk about that too. And this is a negative signature of several tens to hundreds of nanotesla. It's always negative. DST always goes down. It's convention. Computed from the H component at 4 near equatorial stations that are spread in longitude, and I'll show you a map soon. And then we talk about the high latitude ionospheric current systems. These are the auroral electrojets. These are measured, and you've probably seen me talk about them, the AL, or AU, AL, AE, and also AO indices. They're all related. The perturbations are a few hundred nanotesla up to 2,000 nanotesla. So these things can be massive, and I'll show you some interesting examples. These are computed from about 10 auroral stations, a little bit more, from the maximum positive and negative perturbations to the horizontal component, okay? Now, notice I don't have the Kp index up there yet, because it's its own animal. The Kp index is derived from the maximum range of either of the 2 horizontal components over a 3-hour interval and focuses on mid-latitude deviations and perturbations. So it really isn't, the Kp index doesn't really separate a single current system. It's kind of, and that's why we call it the planetary, oftentimes a Kp, it's a planetary index. We're trying to get an idea of what the planetary disturbance is. But it is very heavily weighted towards mid-latitudes, and we'll see why in a few moments. So this kind of gives you an overview of what we're going to dive into. And now that you have an idea of what the current systems are, you'll understand a bit more why they work so well. Okay, so here's a sample solar quiet ground magnetometer reading. And here for kicks is the current system. You can see the solar quiet current system in the northern hemisphere and the southern hemisphere. Obviously, this is noon. And then back on either side is night. So this is where the sun is. Anywhere you see those circles, that's where the sun is. And so this current system causes slow, as the Earth rotates, this current system stays where it is, because if the sun is here, it's going to stay right here. And as the Earth rotates beneath it, you're going to see you're going to go through part of this current system and then the other part. So you're going to see maybe northern perturbations and then southern perturbations. And that's exactly what we end up seeing. When you look at all of these different stations, and you may or may not be able to read this, but this is an old plot. These are latitudes. They've got them listed from high latitude, about 64 degrees, all the way down to the equator, right about here, and then goes to southern latitudes. We've only got a few stations in the southern latitudes, but you will see something very interesting. Right about at the equator, everything reverses. Makes sense? You got the current systems reversing. So you'd expect at the equator some magic would happen, right? And that's right about here. So for the northward component, as you can see, delta x, here's going to be delta y and delta z. So you've got the northward, the eastward, and the vertical component. You've got, all right, and you've got, okay, you've got, sorry. I was just thinking for a second if I wanted to translate something for you, but I think you guys know x, y, and z well enough now. You can see that there's a southward perturbation, or I mean, yeah, this is northward, so southward perturbation and then northward. And you can see that at high latitudes, and you can see it continues all the way down to about here. Then things begin to change. It gets a little bit different. Things begin to get kind of wonky, and they actually get very strong right about in this, I don't know if it's this region here, I think it's right at the equator. There's something that peaks, and you're hitting a current sheet right there. And so you're getting yeah. And so you're getting, I don't want to say current sheet, you're getting there's a break, if those are the currents, I'm not sure that's the magnetic field or the currents, but you're getting a discontinuity here. And so you have a very strong magnetic field perturbation in that region because of that, because you have back-to-back currents that are pointing the opposite directions. And so then when you go into the southern hemisphere, now it reverses. Instead of having a south wiggle first and then north, now it goes north first and then south. And as you go lower in latitude, those wiggles get stronger and stronger and stronger. So that's northward. Eastward, you see a similar kind of thing, where you see a certain type of, what we call a bipolar or bipolar reversal. It goes one direction and then reverses. And you see that all the way down to about the equator. And then it reverses. Instead of going up and then down, now it goes down and then up. So same thing with eastward, and it'll do the same thing with the vertical component as well. Okay? So you see that once again. So this is over a local time of one day. So you have midnight, here's noon, where you get the strongest perturbations, and then it goes back to night again, where things kind of die off. Again, midnight, noon, nighttime, midnight, and the same thing here. So this is one day, and you can see the variation is very smooth. And so that's what this is what you have to subtract. This is the solar quiet variation that has to be subtracted from magnetometer readings prior to even thinking about the disturbed stuff. Remember, this is just quiet time. Now here's a lunar daily variation. So we had one from the sun, and now we have the L variation, which is lunar. The lunar variation, it's a quiet current system, and it also exists because of the E region of the ionosphere. That's where all the current is being carried. The lunar gravitational tides can drive atmospheric variations that we call tidal winds in that region. And this is about 10 to 15% of the SQ variation, so it's much smaller. But it's also smoothly varying. And this also has to be subtracted out. So again, here's local time. Again, we've got three components. The H, this time it's an H component, Z component, and D, the declination. And you can see, at least in the components, you can see where the latitude. This looks like it's a model. I'm not sure this is actual data, but this is a model of it. And so here's 60 degrees all the way down to the equator, and then in southern hemisphere back up to 60 degrees. And you can see these variations are strong at the equator, but they die off a little bit, but they reverse. The northern hemisphere and the southern hemispheres, well, sort of reverse. I don't even know. Look at this. Okay. Because I have not checked this. Boy, they are very strange. Okay, so you can tell, and I do not know the model, I'll tell you that much. I didn't even know until I started really digging into this that there was a lunar variation. I knew SQ, I grew up with SQ, but the lunar variation was something I had not really known about. And probably because people haven't studied it for so long. unless you're an ionospheric physicist. But as you can see, they are different. Here at the high latitudes, they look the same, but then they change. Look at this. It flips at about mid-latitude. It completely flips. What was up, down becomes down, up. Okay? And then, you know, you get the big variations at low latitudes, which I would expect. But then you've got these strange reversals. So horizontal component, vertical component, and then the declination angle. And I'm not really, I can't off the top of my head think of how that would vary, but at any rate, you can see that there is a decent amount of perturbation here, and these again being smoothly varying and happening during quiet times need to be subtracted off of magnetometer data in order to isolate the current systems that we really want to get to. And those current systems are the ones that are active during solar storms. And so in order to be able to derive the KP index, first we had to understand all these different current systems that are there, and then we had to say, okay, how do we eliminate the stuff that's just there all the time? You know, we have seasonal variations, diurnal variations, hourly variations, we have latitude variations. We got to get rid of all of that stuff. So back in 1949, I think it's James Bartels did a lot of work, and he came up with all sorts of studies that and analyses that enabled him to create tables of these other quiet time variations that then you could, in actual numbers and values, that were latitude dependent, seasonally dependent. You know, he had them centered on the equinoxes, he had them centered on the solstices, and he had summer. I mean, he had, I think there's 3 different time periods, equinoxes, solstices, and oh, right. I think he had winter. He had equinoxes were the same, but he had the summer solstice and the winter solstice were 2 separate ones, or were not the same. So I know he has sets of 3 lookup tables, and that you have to subtract them off depending upon what month of the year you're in. And then, of course, it's all latitude dependent. So once you subtract all that stuff off, then you're able to look at what you have left as being something that could be used as a for a KP index. So getting to that, here's the KP index. It is a 3-hour time resolution, and it's a quasi-logarithmic scale, and I'll show you a little bit about it. It's done in basically a third of K units. Most people only know that KP goes from 0 to 1 to 2 to 3 to 4 all the way up to 9. Well, that's not necessarily true. There's actually a 1 minus and a 1 plus, a 2 minus and a 2 plus. Believe it or not, there actually are segments. It's actually segmented into 28 different values. But the KP that are typically used, or KP that is typically published by SWPC and by other parts of the world, they don't necessarily, they'll put those numbers in a table, but they won't necessarily plot it. So you'll actually see when you go in to look at KP values, you oftentimes will see the plus and the minuses. And a lot of people kind of scratch their heads and go, well, what does that mean? When I look at plots, I don't ever see pluses or minuses. It's actually because the original definition of KP actually had 28 values, not just 9. So the index is available from 1932 onwards, and we'll talk about why these time frames are so relevant, and I keep bringing them up. But we'll talk about that near the end. Now, they're designed to characterize the intensity of the geomagnetic activity on a planetary scale, okay? But they're, because remember we talked about not being able to separate the ring current from, let's say, the electrojets totally. But they're heavily weighted to Europe and North America, and part of that is historical. Here's a map of them. You can see here's around 60 degrees latitude. They're anywhere between 40 and 60 degrees latitude. Here's 40 degrees in the south. There's a couple stations here. And then all of these are very much in Europe and America and Canada. Well, that's because that's where space weather studies started. You know, they're heavily weighted because this is where a lot of the work started. Obviously, you're not going to have a lot. Well, I can't say this, but you know, in some of the underdeveloped countries, you may not get a lot of money or a lot of people who are interested in studying that stuff. So it's historically, we understand that the KP index has far more weight in this region than anywhere else, and there's a reason why we don't change that. Now that it's been established, we leave it as such because if we were to change the stations, then how would we be able to look back at KP and it's going to be a different index. So if we wanted to change the stations, well, we're going to have to change the index. So we keep the KP index going, and it's got a very long history. So it's 11 northern stations and 2 southern stations between 44 and 60 degrees geomagnetic latitude. Like I said, it's mid-latitude, so it captures some of the ring current effects. It captures some of the higher current effects from the auroral electrojets. And it is the arithmetic mean of the 3-hour standardized K indices. Now, when we talk about standardized K indices, we are talking about stations where you have subtracted off all that SQ variation, the L variation, all of that. Oftentimes you will see that represented as KS, typically a small k and a little sub s. That is how they represent the standardized K. And these are local K indices that are, from the magnetometers in that region. And as a matter of fact, if you go to the USGS, you can see, I think they still have some of the local K indices available for you to look at, and I'll show you a few of those. Even NOAA and SWPC has a few of those stations readily available, so you can see the local K, and that is a KS. Now, if you take all the KS's from all of these stations, add them up, and do the arithmetic mean, boom, you've got the KP index. Okay, but it is a 3-hour interval, which means if there is a disturbance anytime in that 3-hour interval, you may not know it for 3 hours, which is why it's horrible for aurora. If you want to get aurora, if you want to get a sudden storm commencement, if you want to catch the beginning of something, which is oftentimes the most intense part of a storm. As a matter of fact, I think we've got a solar storm that it's brewing right now, and it may be getting to that point. But I guarantee you, some of the best action will have already passed by the time KP jumps up. Why? Because it's a 3-hour delay. So if you're looking for now time kind of reactivity, KP is not your thing. What you need to look at are either local K indices that are giving a running, a running measure, that are kind of doing, maybe they've got something where they're averaging over 3 hours, but they're putting it out every minute. The higher resolution that you can get up, even if it's a rolling average, the better off you are. But if you can get, obviously, straight magnetometer readings, that is the best bet, because you can see disturbances right away. But waiting for the KP to catch up to you, not a great idea. Okay, let's see. So the standardization is achieved using the tables. Okay, and there we have that website in Potsdam that is really good. And again, I've got the link. You'll see another one. You'll see a link to it here in a moment. And that was, you'd have to subtract off that stuff for each observatory, and it was Bartel's his magic paper in 1949 that talked about how that was done. So you can get access to that, and this website, the GFZ website, will show you all of that. I mean, it's a fantastic historical website that talks about all the work that Bartel's did, which is non-trivial, and really revolutionized how we use indices. So related geomagnetic indices, you've got that shouldn't be capital, that should be small. Small AP, big AP. Small AP is 3 hour, big AP is 1 day. This is obtained, a lot of people use the 1 day average. This is the daily average of 8 little AP values. So you can get an AP, believe it or not, that is on the same order of, and same time resolution as the KP index. It's just little AP, not capital AP. The capital AP is the 1 day average, so you can look at a longer time scale. So those of you who, you think KP is bad, with it being 3 hours delayed, try using AP to forecast or to notify yourself about aurora. Why bother? It'll be a day gone before you even know it happened. Again, this is the AP index is a daily average of AP values obtained from KP, and I'll talk a little bit more about that in a minute. Then you got CP, C9, C48. There's so many different indices that are derived from the KP index. Just organizing things in a different way, taking the quasi-logarithmic scale and turning it linear. That's how you switch from a KP index or a K index to an A index. A's are linear, whereas K is not. There's just all sorts of things that we do to look at this stuff. So here's a bigger idea of the map. I wanted to do this because I figured that you probably weren't going to see it very well with that small thing. So you can see, look at how clustered these are. These stations are all over Europe and up into Sweden and Norway. We've got some in the United States. We've got some in Canada. We've got a few in Australia, and I thought there was more. Anyway, so yeah, I thought there was more than that downstairs, but I guess not. Yeah, so as you can see, it's incredibly heavily weighted up in the northern hemisphere, which is kind of sad. But, you know, if we want to rectify that, we're going to have to start a new index, which I'm sure we will. I mean, as we begin to learn more, and as we get more areas in these regions that we can populate. I mean, you can see there's not a lot of land down here, so that makes it difficult as well. We kind of populate whatever land we can find, but nonetheless, there, you know, who knows? Our technology may be able to get us so where we can actually have stationed buoys, either, you know, tethered or something like that, where we can actually have a magnetometer. I don't know how we do that without it, you know, being jiggled by the water, but you know, these are problems that we could potentially eventually solve. So yes, are these indices perfect? No, but they were what we could do at the time. And again, so if we're looking at latitudes between 40 and 60 degrees in latitude, we're talking a little bit of influence from the ring current. We're talking a little bit of, and we're talking a bit of influence from the field line currents, and the partial ring current. And so we're talking essentially auroral electrojets, not too much, but basically stuff that's going to be kind of affected by the ring current, kind of affected by the electrojets, kind of affected by, you know, the set of currents that's between brown, green, and blue. So a few different processes. Will we get the substorm current system here with all the really auroral electrojet stuff? Probably not. And we'll see that when I start talking about the AE index, because this stuff is just too far out. You know, we'd have to be up in here to be able to get those to get those get the effect of those current systems. Here is a list. I'm not even going to go over it. This you can find on the websites that I showed you earlier. And I just love it. There's one called RSV that says Rude Scove. I love that. That's classic. I started laughing when I saw that. So I thought I'd share that with you. And here is GFZ. This is the website and here's the link to the GSC website that goes in depth about what the KP index is. As you can see, here's some text here. It goes into how all the 28 values are obtained. As a matter of fact, here's a key, a legend to it. You can see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but 0 plus, minus 0, plus 0. I mean, you can see these are, you know, so you have a 0 plus, you have a minus 1, you have a 1 plus, a minus 2, and, you know, they call 2, 0, 2 plus, you know, minus 3, 0, and then a 3, 0, and then 3 plus. It is a kind of insane how he did this. And then he's actually got this bar diagram where these S's show sudden, or this actually shows solar storming, and the triangle will be marked here if it's a sudden storm commencement. There's all sorts of really cool things that Bartels did back in the day. And you can go over all of this on the GFC website, which is just, if you are a history buff, I would strongly recommend it. It gives you an appreciation for what Bartels did and how difficult these indices are really to create. Because you can see all the tables and everything else that, the lookup tables and everything that you have to do to standardize the K indices. So let's get at it, okay? This is a KP index chart. You ready? Anybody recognize this? This is KP. You guys haven't seen this before? You sure? It's the musical diagram. These are the way KP indices used to be drawn, believe it or not. And it's called a musical diagram or musical bar sheet or something like this. You can see once again there's that key down at the bottom, and so here is days in the solar rotation interval. So that's basically 1 to 27, and so every solar rotation, this is kind of a Carrington type map. And here's from June of this year. There's 19, 20, all the 25, 30, all the way into the July, the 15th of July. Here's July to August, August to September, September to October, October to the end of October, and that is, believe it or not, this year. So that's what KP has looked like since June of this year, and these diagrams are still being made today. Is that cool? They look like music notation. It looks like stave notation, and that's exactly how they did it back then. Long back in 1949, we didn't have computers. We didn't want to just look at numbers. We wanted to look and have some visual representation that gave us a feel for what was happening. And as you can see, the strength of the KP, once you got a storm going, you can see immediately where the storms are, right? So this is how they did it back in the day. Thank goodness we don't have to do this anymore. We have something that looks a little bit more familiar. Well, hopefully it looks more familiar, even if it's incredibly boring. This is today's. I took it off the web just last night, so it was just beginning to be December 1st in UT time. And we are pitifully quiet. I think that's changing. If anybody wants to look up what the KP index is doing right now, I might look it up on my phone while we're chatting here to see how the storm is going. But we have been at 0 for a very long time. Everything is in the green. We know that anything less than 4 is going to be green, so anything less than active conditions, I call them basically normal or quiet. Zeros and ones are typically what I would call quiet. 2s and 3s are what I call unsettled, and that's still be in the green. When we get to 4, that's active conditions. When we get to 5, that's storm levels. Above KP of 4, you're going to see red, and then it stays red all the way up to 9. And right now you can see we are pitifully quiet. But you notice there aren't zeros and ones. There's not a 0 plus or a 1 minus, or you don't see any of that. They've kind of just gotten rid of that for these types of plots. And is that good? Is that bad? I don't know. I think it's more convention. I think the reason why we're dealing with that, yeah, see, we haven't done anything. Here's, I don't know if you guys can see this, but that's the current KP right now. So we've gone up to, what is that, 2, 3. So we're right now up at unsettled conditions because we do have a storm going on, and it's just ramping up really slowly. It looks like the speed is now sitting around, solar wind speed is around 400 kilometers a second. Okay, so that's good. So that means that right now, amateur radio operators should be enjoying life because it's not too busy yet. Unsettled conditions typically give us some good ham radio propagation, but we're getting it to 400 kilometers a second, which means that we're probably going to start seeing aurora brighten, and ham radio may start going downhill soon. Not quite yet, but soon. Anyway, getting back to this. So here's the KP index for essentially from the 29th up to essentially the current time. It's got a few areas here that are missing, but when we look at the right, here is the K indices. These are the standardized K indices for the Boulder station, the Fredericksburg station. Here's our estimated planetary. Whoops, hopefully something fell. I think we're still okay. Let me make sure. I had a piece of tape fall, and it looks like our thing is still doing okay. So here's the Boulder station, Fredericksburg, estimated planetary, and College station. And this area for the estimated planetary, it corresponds to this. This yellow highlighted area is the panel, is from the 29th on to the 2nd. So this right here is what we're looking at here. But as you can see, we have other stations, this being the planetary. So this is the 13 stations that are being averaged. These stations here are local K indices for that area, and that's the KS. So if you happen to live near any of these stations, by all means, don't pay attention to this. Don't pay attention to the planetary. Pay attention to your local station, because that's what's going to tell you what's happening just above you. And that, as we've learned, when you map things, to the latitudes, you're dealing with whatever current system or whatever disturbance is right out at a region that then maps to what's going on right overhead. And when you do that, and you happen to have a station right there that can tell you what's going on, that is the station or the set of stations you want to pay attention to. KP is going to average everything over the globe for those 13 stations. So it's going to smear out what's happening at Fredericksburg or at Boulder. okay? So when you look at these things, kind of keep that in mind, that the planetary KP it's great, the planetary K, which is KP, is great for a lot of things, and it's great for some science that we do. But it's not necessarily good for looking at local impacts, and it's definitely not good when you want high time resolution. Now, getting into a little bit more interesting K, here is from the most recent, or here's from the 2017 storm. Excuse me. I thought I put the, I guess I didn't. Okay. Here's from the 2017 storm in May. This was this was a storm that got to a G3 level for a short while, and you can see again we have zeros. It was quiet, and then it jumped to unsettled conditions, and then it jumped to a KP of 6, which is a G2 level, and then it jumped to KP of 7, which is a G3 level, and each one of these bars is 3 hours averaged, right? So 1, 2, 3, 4, 5. So we had 5 times 3, 15 hours of storming at whatever level we had here. Now, if we flip over to the K indices, the standardized K indices, except for this panel, this is the planetary panel, this yellow highlighted area is the same as what I'm showing here. And you can see again, here's what we got for averaging the stations. But look what Boulder got. Boulder only had a K of 6. And Fredericksburg had even less. They had only 2 Ks of 6 and Ks of 5. Whereas College had a K of 9, which College is a little bit sensitive. But they jumped to a huge K. So see how different their K indices are? But these are all averaged into, these are three stations out of 13 that are averaged into the KP. So even with just looking at 3 separate stations, you can see how radically different they are. Your local variations are going to be different than what a KP will give you. And just to give you an idea of what this storm did, this little G3 storm, here are some of the impacts. We had back here, here's a global view. You can actually see the delta B changes. So this is the delta magnetic field. These are the perturbations that we're talking about. And they got to be pretty strong over North America, over here past Antarctica, and a bit in the south. And apparently British Airways, the currents up here were so strong. And remember, we're looking at magnetic field perturbations, but they're linked to the current systems out in the magnetic shield that are being amped up. And so because of that, they caused these huge perturbations. British Airways had to cancel all their flights, and there were some power outages that occurred in certain places. Here's a blow-up of just over North America, and you can see over the Canadian region from anywhere from 40, so here's 45 degrees up to 60 degrees. Remember where KP we were talking about? From about 44 degrees up to about 60 degrees. This is exactly the area that the KP index pays attention to. And look at this strong geomagnetic, the magnetic field variation. So this was the North American view, and there were power outages because of this storm that occurred in Aberdeen, Illinois, okay, and Kenosha, Wisconsin. And these are reported as from NOAA. So there have been, even with the storms just recently as last year, there have been power outages in the United States. So do you think a power grid company is going to look at this? KP is a great indicator for power grids because 3 hours they can probably handle, but they can at least start getting ready. Do they need to look at an immediate index? Not necessarily, but KP is probably pretty good for them. It's simple. It doesn't come out too much. It doesn't tax their people. They don't have to do a lot of training, but it's a great index for them to pay attention to. So hopefully that gives you an idea. And now, let me ask you, let me show you something else. Since we see what we see here with the K indices, and you see how it can be utilized for things like power companies. Let me show you a storm that was a little bit stronger. Anybody remember the Halloween storms? Hopefully. So this was the 2017 storm in May. I'll show you the KP index with that, and I'll put it next to one of the Halloween storms. And maybe you can get an idea of how big solar storms can get. What do you think? Think we had some issues? Yeah. This caused power outages in the United States. This caused satellite anomalies and failures. There were power outages. There were airports that had big problems. And look how many hours it lasted. We had 3 days of very intense, nearly off scale, if not off scale. So the KP index, it's not that it's not useful. In situations like this, it can be extremely useful, especially when a power company knows what to expect from something like that. And they say, okay, how do we mitigate something like this? In a glance, you immediately understand the difference between these two storms. That is part of the power of the KP index. It captures both the ring current to some degree, it captures the auroral participation, it captures things from multiple current systems distributed across the Earth, right? And it can be an extremely powerful tool for the right setting. Now, of course, anybody watching Aurora at this time probably didn't need KP. It was all over everywhere. I think Aurora reached Los Angeles. It was pretty intense. So moving on. So what you just saw was a superstorm, by the way. It's not a Carrington class event. That was just a superstorm. Carringtons are even bigger, which I don't even want to think about. So, okay, so the geomagnetic A index. So here's the little AP I was talking about and big AP. These are KP-derived indices, and I'm not going to go into these in any great detail because I think you understand already what we're talking about. Here's the KP index, 0, 0, 0 plus, 1 minus, 1 0, 1 plus, 2 minus. These are, all the way up to, I'll keep going all the way up to 9. Okay, so I've got 2 rows here. The AP index just linearizes it. It just says, okay, I don't want a quasi-logarithmic scale. Give me numbers. Just give me real numbers. So as you can see, these seem kind of haphazard, but really they're trying to make the scale, instead of being logarithmic like a seismic scale, they're trying to make it linear. So AP will go from 0 to 400, whereas KP goes from 0 to 9. It's the only difference, really. And if you want a 3-hour average AP, the little AP, then it's 3-hour average. If you want to capitalize it, well, then you're going to take those 8 values over the course of the day and you're going to average them. And that will be your capital AP and you get a daily index. That's it. It's really not that complicated. So again, KP is a 3-hour averaged index. AP, capital AP, is a daily index. The numbers are different because one is a linear scale and the other is kind of a quasi-logarithmic scale, but they both are based on KP. And they both give you a slightly different view of the same type of data. Here is the November 3rd storm we had just recently in KP. Here are daily A indices from November 1st all the way through December 1st. You can get a whole month at a glance. And this whole KP region now reduces to just this. So basically you're looking at this bar, something like 35, averaged all that stuff, essentially. And, linearized it. It's not a scale from 0 to 9. It's a scale from 0 to 400. And it linearized it and made it just this one bar is almost essentially what you're talking about. That's what all this is here. And is this good for real-time understanding? Is it good for climatological stuff where you're looking at things over a much larger baseline? Scientists who want to understand longer-term variations will use the AP index. It's much more useful for things like that, especially when you're trying to understand how things change over the course of years, right? Would I use it as a daily index? It's not going to give you anything. No. For that, you want to go to the higher resolution stuff. And for nowcasting, you don't even use KP. So hopefully that helps you understand. All right, so now on to the next really interesting one. This is the Auroral electrojet. We've got AE, AU, AL, and AO indices. Okay, these are 1-minute time resolution indices, and they've been available these have been available on and off, 1957 to 65, but only AE. From 1966 to 75, they've been available, and then 1975 available again, only AE and AL. I mean, there's just all these little sporadic breaks. Well, stations go up and down. It's hard to maintain this stuff. There's all sorts of reasons why there are sporadic outages. But these have been the labor of love for many scientists over many years, and we've managed to keep them going because they're very relevant and very important to space weather forecasting and nowcasting, as well as understanding, of course, heliospheric sciences. It's an auroral index, and again, it's working on the horizontal components and the disturbances in those. It was derived to monitor the magnetic signature of the eastward and westward auroral electrojets in the northern hemisphere. These are being driven mainly by the tail currents, the current that's way out in the back. You get substorms that come in and drive particles that come down into these region 1, region 2 currents, and the substorm current wedge and all this other wonderful stuff that is way beyond the scope of this. But there are 12 observatories in the northern auroral zone, and it's created by superimposing the horizontal components of these magnetograms from these stations. And then there's a mathematical way of dealing with how you get these different indices. And I probably should have written this out, but I didn't. The AU is called the upper index. The AL is the L for lower index, and AO, I forget what O stands for, now that I think about it. But there is a way to how you define them. Is these are two separate indices, and then you've got AO. Okay, then you've got AE. Right, AE is made by subtracting these two, the upper and the lower envelopes, and AO is made by adding the two, AU and AL, together and then dividing by 2. So there are specific reasons why we do this, and I won't get into those specific reasons. Again, more scientific information than you need to know. But you can see these stations now are located at much higher latitudes than where we were for the KP index. The KP was more mid-latitude down here. These are located way up here, closer to 60 degrees and clear up to 80 degrees. So again, blowing up the map for you, you can see as we go higher in latitude, right? What do we say? That map's further out. So now we're past this region. We're out here. We're getting out to the part of the region 1 currents that are further out, and of course the substorm current and the substorm current wedge. These are mapping a much higher latitude. So this is where we see the action from the Earth's magnetotail. This is where you see the slingshot effect when you have things like reconnection. You stretch out that tail, you cut it, and the tail snaps back like a rubber band and slingshots particles up into the northern hemisphere, down into the lower hemisphere, or the southern hemisphere, and then create these currents that shoot down into the upper atmosphere and cause aurora. Pop, 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 pop. It's like a pea shooter from the Earth's magnetic tail. And these types of things do not require these types of actions of the tail. These are reconfigurations. Can they happen during a big storm, like that superstorm we saw with Halloween? Sure, they can, but they don't have to. They don't have to be when the ring current is being energized. They can happen with much smaller inputs. As a matter of fact, sometimes no input at all. Sometimes the Earth's magnetic shield has just enough energy in just the wrong places that when it reorganizes, it does what we call dipolarization. And it will dipolarize, it'll slingshot particles forward just to make its own magnetic field less energetic, less stretched, less bent, less irritated. And so it will reconfigure itself and drop its energy and shoot all that extra stuff towards the Earth and create these current systems, and these stations are the ones that catch it. So what does it look like? Here we go. So this was the 5th of November. Remember that storm I showed that had a small, the KP went up to it was a G2 level, it was a KP of 6, I believe, for just a moment. Only lasted for less than a day. This is what the AE index and the AU and AL indices looked like. So the AU is the upper envelope. You can see this line being here. The AL is the lower envelope. AL is negative typically. AU is positive typically. And you can see these. See how it jumps out? See the bursts, the bursty stuff, right? This is a local time, or no, this is universal time, starting of one day up to midnight. Here's noon. And then down here, you've got the AE and the AO. The AE, remember, is the envelope between these two. You subtract the two, and you get this line here. And the AO is when you add these two numbers, and then you cut it in half. And that's this number here. Okay. Now, really, the rule of thumb is about 500 nanotesla. That's when you start seeing good substorms. It's just a rule of thumb, and if you want to know where I got that from Dr. Joe Fennell at the Aerospace Corporation, who is a fantastic scientist, knows all about spacecraft charging, which these things do, and he knows a lot about magnetospheric physics. He's probably forgotten more than I will ever know in magnetospheric physics, a true guru. And he said, rule of thumb, 500 nanotesla. When you get anything above 500 nanotesla, you're probably getting some decent aurora. But notice that it's bursty, bloop, for a short while, and then bloop again for a short while, and a little bit here, up and down, up and down, up and down, right? You're not going to see that in the KP index, right? You'll be lucky to see anything at all. Up in the beginning of the day, you probably weren't seeing much, and then only when you got to about here, did KP say, oh yeah, by the way, it's storming. You guys might want to look outside. But then you go and look, and you're down looking at this period. And you're like, well, there's no aurora. And then a little bit more time goes, and it goes, and KP says, oh yeah, it's really storming, so okay, I'll look. And you look here, less than 500. And you're like, what is the KP index mucking with me? I don't get this. There's nothing going on. And then a few minutes later, there goes the aurora again. So again, the AE index, this index, not only is it higher resolution, but if you want to look for aurora, and you can use this for the southern hemisphere too, because they're conjugate points. It may not be perfect for you, but at least it's something. It's better than not having anything at all. If you can get local AE stations, I would strongly advise you to do so. But this is from Kyoto. I take a look at these stations, or at the AE index, to help people nowcast aurora. I've helped them nowcast aurora in Canada from Canada, Iceland, Sweden, Tasmania. I've helped do nowcasting for aurora. Say, okay, in 10 minutes you're gonna get something, and oh yeah, you should be seeing something right now, and oh no, you're not. You shouldn't be seeing anything. You're gonna have to wait a few more minutes. I've done that with these plots, and it really does help them. It may not be perfect, but it helps them a lot more than KP index will. So, again, the rule of thumb is 500 nanotesla is when you start really seeing some substorming. And when you get to the point where it's completely red, then you know you're in a geomagnetic storm, a big full-blown storm. But otherwise, you'll see little bursty stuff, and that's when aurora will brighten, and that's when it will dim. A lot of times you can see when you get stuff like this, especially near the end of a storm, that's when aurora will pulsate. That's also when aurora will, when you can get the subauroral arcs, also known as Steve. So you can see a lot of stuff from this. And just for fun, here's that May 2017 solar storm, the one that caused the power outages, and you saw those big delta B perturbations. Here's what it looked like. Now, instead of just 500, which is, let me go back here. You can see here we got mainly 500 was about where things were. It kind of peaked over 1,000, but not really. This is the AE index I'm looking at specifically. Most of the time just over 500, right? But a few peaks over 1,000, but not very much. So that was early November storm. In the May 2017 storm, hopefully you can see this, here's 500. We are consistently above 500, starting at the end of the 27th. There's 500 right there. We started above 500 and stayed above 500 for almost an entire day. We finally dropped back down below 500 here. And we were peaking almost off scale on this map, which is about almost 2,000. That's where the peaks were. So that's where that one was. And that was the one that caused the power outages and the British Airways to shut their flights down for a while. And now, what do you think this is? I think it might be that superstorm that, remember when KP was like all red, there was nothing there for that Halloween storm? This is what the AE index looked like, or the A indices looked like. So this was the 29th of October, this is the 30th of October. Can you see that? It's off scale. Now don't worry, it wasn't breaking the magnetometers or anything. These are just provisional plots. So They haven't been rescaled so that you could see how large the numbers actually were. But 500 has been decimated. I mean, here's 500. There's like a time that we're not above 500. If we look down here in the AE index, I finally get a little bit of a break right here. But in this big part of the storm, we don't even dip below 500. So Aurora was crazy busy, and the current systems were crazy busy. The magnetic tail was just firing and firing and firing and firing and firing constantly because it's trying to shed energy. So all of the current systems were jacked up. That's why KP looked a mess, AE looks a mess, everything looked a mess. All the current systems were just absolutely going crazy. And that's why we had satellite failures, and that's why we had anomalies, and that's why we had power grid failures, and that's why we had all of this stuff, because all of the current systems were overwhelmed. Okay, now the DST index. I'm not going to spend a lot of time on DST. This is more of a scientific index. Do I think you need to use it? No, really, unless you are a big Steve chaser, unless you really want to know when pulsating aurora is going to happen ahead of time, then you'll have a little bit of a learning curve, because DST tells us a lot about the ring current. But there are certain phases of storms and substorms that are far more scientific in nature, and you almost start needing to learn a bit about the physics of the storms themselves to understand why do these things happen during the recovery phase and not the main phase of the storm. And DST helps us learn about that type of thing because we're actually watching things. We're actually watching the onset and the main phase and the recovery and how long it takes for the DST to recover. And there's all sorts of little aspects that we can learn by studying DST, but we get lost in jargon very quickly. And as you can see, it's a low latitude set of stations from 40 degrees to about 25 degrees, or 20 degrees actually. And there's only 4 of them. There's only 4 stations that are monitoring it. So, and it's a 1 hour time resolution, although you get a running average more at a higher resolution than that. It's what we call an equatorial index, and it's available from 1957. But it was designed to monitor the magnetic signature of the magnetosphere currents, including the ring tail, or the ring current, the tail current to some degree, and the magnetopause Chapman-Ferraro current. It's calculated from the 4 low latitude observatories, which are sufficiently distant from the auroral and the electrojet regions, so it isolates. That's why we only use a few stations, because they're low enough that they are almost completely isolated from all of that noise we saw in the AE index. Okay, so it's distant from the auroral and the equatorial electrojets to inhibit the noise, and then they're computed. It gets a little tricky how the DST index is created. You get contributions to the horizontal field from the background, the non-transient field of the core and crustal origin. And I don't even pretend to understand all of the issues. I am not a big DST person because I don't study, I'm not a magnetospheric physicist. So the origins of DST and all of the details I am not completely familiar with. But we have to, again, we have to subtract the daily variations, and we have to really worry about normalizing things to the dipole equator, because at these really low latitudes, we start getting into there are other issues. Keeping a baseline, a solid baseline when it comes to DST is very difficult. We also start dealing with induced currents, and those induced currents on the ground are reflected back. We can actually get that measured, or measure those in currents on the ground, and they actually contribute to this. And that is part of the issue that people are beginning to have with the DST index. They would actually like to separate it into the EST index for the external source field and the IST index for the internal induced field. And there are papers on this, and if you guys want me to put them out or share them with you, I can. We have issues with the induced field being something like 1/3 of the external field. And so it's adding to DST. And do we need to take that, because those fields are, they're important to know, but you don't want to have them slapping together in the same index. Plus, because of the way Earth is not a perfect conductor, the induced field that's in the ground, we're talking about like GICs, the ground-induced currents during geomagnetic storms, that current it's lagged. It lags the external current, and so when you add it back, when you're actually measuring the stuff on the ground, you're not even measuring things that are happening at the same time. There's a shift between the two. So you get the external source current, and then you get your current system, and then you get the ground-induced current system, and they're overlapping each other, but they're offset because Earth isn't a perfect conductor. And so that causes, you know, a smear of effects. And so people are discussing new indices in which the EST and the IST index that are kind of, in a sense, breaking apart the DST index and making them more usable for these other types of studies. And that is still underway. But as I mentioned earlier, and I think as I mentioned in the description of this webcast, that as we learn more about space physics and we learn more about what our magnetic shield is doing and how it's affecting us here on the ground, we're able to get smarter. And so we're able to derive even more indices that then will focus in and continue to focus in on one thing or another. And that is extremely important to us. No, you...
I'm just asking if I could use the internet.
No, Evie. My daughter, sorry. I remember I said I kept the door open, so she felt she could come in.
Wait, can I use
So,
the internet?
no, Evelyn.
Oh, I'm sorry. I'm already on it.
So, pardon me.
I'm not going to use any more internet.
I don't know if you can hear her. She's continuing to dialogue with me. My 9-year-old daughter is going to be an actress, I swear. Either that or a comedian, like her father.
One question.
No, Evelyn, I am busy.
Can I use the iPad internet?
No.
Play on Roblox?
Okay, so here are the 4 stations. Here are the 4 stations and at low latitudes. And again, being at low latitudes, I probably should have had the other diagram in here. But being at low latitudes, we are really talking about magnetic field lines that are very, very close to Earth. And so we're going to catch the closest current systems that are there, and that is definitely the ring current. So that's where we're getting the main contribution, is from that. And here is a couple plots of DST. Here's from that December 5th storm. You can barely see it. This is a DST that goes from 0 to minus 500. See that little guy? See it dip down and then back up again? Here's the onset, main phase, and recovery phase up in here. Again, I'm not going to go into the details of what they are, but you can barely read them. It's about 50 to 70 nanoteslas. That's it. That's as far as it dropped. And that was a November 5th storm that we had just recently that brought us some decent aurora. Here's that May 27th, 2017 storm that caused power outages. Now you can see it actually jumps up at the onset and then slams down pretty hard. And this is one of the classic types of signatures from DST. And then we got this kind of a slow phase, kind of recovering. This is the recovery phase of the storm. But you can see the maximum, it went down to maybe 125 for DST, minus 125. And you can see that you got a nice little signature there. And then there's some other stuff that continued coming back up. And this tells scientists, this is what scientists use to be able to correlate different aspects and different processes that are going on during these big storms. But these are how the ring current was behaving, and kind of reflecting the energy of that ring current. And then here's that October 2003, the Halloween storm. If you can see it, do you see this monster? Hopefully you can. I'm completely out of the page here. Hopefully you can see that. This was a monster. It had multiple type onsets. It was insane. This is actually several storms that occurred. And the peak, or if you call it a peak, the negative peak, was clear down at like minus 375, which compared to the little guy that brought us aurora, peaking at minus 75, look at the difference. So this is a normal storm. This got us up to a G2. This got us up to a G3. And this was off scale. This was a G4, G5, or G5 and above, if there is such a thing. But we were pegged at 9 for quite a while. And you saw what the AE index looked like. You saw what KP looked like. And now you see what DST looks like. Even during the November 5th, I think I showed November 5th, storm for AE, it doesn't show much here for DST. right? There's really not a lot going on. But AE was quite busy. You had a lot of bursts, over 500 nanotesla. You wouldn't think that this caused a lot of aurora, but if you look at the AE index, it sure did. That means auroral propagation to you ham radio operators, and me, ham radio operators, and it means beautiful aurora photography. We had aurora down to mid-latitudes for a short while. But you have to get to a much bigger storm and much more sustained storm to start really seeing decent perturbations in DST. That's because it takes a lot to get down to that ring current and really energize it. So this is kind of neat because depending upon what index you're looking at, it will tell you what you need to know to a great degree and nothing you don't need to know. So I'm going to quickly just go over a couple other indices, but not very fast. I mean, not very much. Some people might ask, well, why don't you just throw all the stations on there? Yes, we've done that. It's called the AM index. I can't even remember how many stations there are. There's a ton of them. There are 5 such groups in the northern hemisphere and 4 in the southern one. We've got different groups. As you can see, they're scattered over many different longitudes from 40 up to 40 and 60, but they don't have low latitude ones, but there's quite a few stations that are there. Some of these stations that have, or some of these indices that have a lot of these different stations, they're not established, they don't have a history that goes quite as far back, like 1959, for example, as opposed to like 1932. The reason for that is because these stations weren't online and they weren't necessarily ones that could be at the same latitude that they could constantly keep there and say, okay, this is standardized enough to stay as a single index. So they weren't started till later. Yeah, and it just says all possible hemispheric discrepancies. So they're trying to cover a lot of bases here with this. Now, what about long-term stuff? The AA index is a classic example of that. You have, it's a 3-hour index, and you can make this a double AA capital and make it a daily index as well. This index, even though it's only got 2 stations, and they're between 40 and 60 degrees latitude, north and south. This index has been available from 1868 onwards. So what's nice is that here's an index, even though it really doesn't characterize all that much, it's something that we can look at for climatology. Because now we have something that goes back to 1868, and it's stable. All those data are stable, and all those data are data that we can trust, essentially, and I'll show you why I say essentially. But because it's comprised of 2 antipodal stations, we can say the southern hemisphere and the northern hemisphere are covered. And then there are conversion factors and all that kind of stuff to deal with it. But these are based on the K index. So was the AM, is also based on the K index. But these stations, we have these stations, these indices, so that we can do different types of scientific studies. Would I ever use the AA index for space weather, not space climatology, space weather? No, never. But space climatology, sure. Sure, if I wanted to look at something over a long period of time and I needed to have a baseline that was stable over centuries, yeah, absolutely. I've used it in the past, as a matter of fact. But here's the issue. And this is part of why Mars Insight is so important. What you're looking at, hopefully it'll restart. Good, it's replaying, okay. So what you're looking at is the strength of the Earth's magnetic field. And you can go to the Kyoto website and get this. This is a model of this is the IGRF model and you can see the year, I don't know, hopefully you can read it. Basically from 1600 to 2100, it's a model of the Earth's magnetic field, and you have contours in different colors, and I don't have the color bar here, but I'll read these numbers here as you see them change. But the color contours are the same strength. So as you see the colors changing, red is the strongest, blue is the weakest. So you said pink rather. That's the strongest, and then blue is the weakest. You're seeing over the course of time, from 1600 to what is projected to 2100, AD, you're seeing the magnetic field changing. Now, what do you think this means for indices? Right? If we have indexes that started at 1600 when the magnetic field strength was a certain strength, and now it's weakening, as you can see as we walk through this. I'll start again and I'll I'll show you how it's weakening. 1600, that says 75. Now it's 70. That says 65. 60. This is 60,000, 55,000. Still at 55,000. So when it starts again, 75,000, and then 65,000, 60,000. So the yellow is 60,000. The 75,000 was the pink, and down in here you're looking at 26,000. So as you see, all the pink goes away, which means we're getting a weaker strength. These are in, I think, in nanotesla. They're getting a weaker strength of the Earth's magnetic field over time. And we all know this. We know that the Earth's magnetic field, its dipole field, is reversing. And so we're seeing that. We're seeing this reversal slowly but surely happening. Do we think the magnetic field's going to go away? No. There are other components of the field that will take over for the short while that the dipole field reverses. So don't worry. Are we going to lose a north and south pole? Yes, it's going to probably be 4 poles. We may go to a quadrupolar field for a while, and there may be poles at mid-latitudes. So we'll have a northwest pole and a northeast pole, a southwest pole and a southeast pole. I'm not exactly sure. Unfortunately, I don't think we'll be alive to see it. But it'll be a fantastic time because we'll have more chances for aurora, that's for sure. It'll be a much more lively sky at that time. But I don't think it's going to last because the poles will reverse and the dipole field will then grow again, just like it always has. And just honestly, like the sun does every 11 years. The Earth does it too, it's just a lot slower, right? We shouldn't get scared about it because the sun does it every 11 years and it comes back. Earth is going to do it again. It's already done it multiple times and life hasn't gone away. So we're going to be fine. But where this is a pain is for scientists creating indexes. We want indices that we can use forever. Well, how do we use it forever if the magnetic field of the Earth is changing so much that the wiggles that we see, the horizontal component changes that we see, that we gauge the strength of storms from and the current systems that drive them, that drive the wiggles. If the magnetic field strength is changing, that means that the wiggles are changing. They're getting weaker. Well, how do we deal with that? How do we look at a solar storm, or how do we look at a current system and say that we can compare a solar storm that happened back in 1800 to a solar storm that's going to happen today? Well, it's getting harder. And not only that, and I'm really close to the end of the presentation, so just in case you guys are getting tired. Not only that, but we're having the magnetic poles moving. Now, I'm sure everybody knows about this. Here we have the magnetic pole. You can see 1900, 1920. You can see 1960, 1980 to 2000, 210, 215 was when this data was. This is projected at 2020, where the north magnetic pole is going to be. Yeah, this is the northern hemisphere, I believe. Yes. Right. This is the northern hemisphere, and so they've taken this area here and cut it out so you can see. The geomagnetic pole, as you see right here, what they mean by this is the actual magnetic pole, the pole that you read with a compass. This geomagnetic pole is the pole of a dipole magnet. If the Earth were just simply a dipole, and we're looking at the dipole component of the field, what's it doing? That's what it's actually doing. And I believe I got that right. That this is what we've measured, and this is what we feel is happening with where the dipole field component of the field is. So, you know, we're seeing big changes because the other components of the field, the smaller components of the field, the quadrupole, the octopole, all these other components that add up to the field, they're changing, or they're becoming stronger, relatively speaking. The dipole field really isn't moving that much. It's just weakening. And as it weakens, the other poles take over, the other components take over. You know, it's kind of like a submarine. You know, a submarine can either pop itself up out of the water, or you can stay underwater and wait for the water to drain. Either way, you're going to be exposed eventually. And in this case, we're waiting for the water to drain, and that water is the strength of the dipole field. As it drains, it reveals what was hiding underneath. And that's why we're seeing this migrate so much. And then here's the southern pole, same thing. We have this little pi wedge here showing where the magnetic pole is, where we've made our measurements, and then what the dipole field is actually doing. And it's not wiggling that much, but we're sure seeing a migration of the magnetic pole because of that, because of the fact that we're seeing the components being revealed, these weaker components that will eventually be, when the dipole field goes away for a short while, they will eventually be what our magnetic shield is. don't worry. We're thinking of colonizing Mars, and Mars doesn't even have a field. So what are we worried about? I mean, we're so gung-ho to go colonize Mars because we think it's such a great place, and Elon Musk is ready to send a rocket there today with people on it. And there's not even a dipole field that you can even shake a stick at on Mars. It's all remnant field, right? And there's still an atmosphere, right? There's still potentially water there and ice. And, you know, people aren't worried about that. But everybody's petrified that for a short while we're going to lose only the dipole component of our magnetic shield, when there's all these other components underneath that will still keep us protected, far more than colonists would ever be protected on Mars. So anytime anybody gets petrified about that kind of stuff, just take a breath and think about Martian colonists and know, hey, we're good. Okay? So with that, and actually that reminds me, let me go back to this for a second. That Mars InSight lander, that does bring me back to the Martian core. The fact that it's looking at the core has major implications for our magnetic dynamo. And what's what I'm talking about here when I'm talking about this pole moving and the dipole field going away. We're seeing a natural process that our magnetic dynamo goes through all the time and has gone through in the past. But the neat thing about Mars is, and actually where Mars is and where Venus is relative to Earth, is that because they're all rocky bodies, like Earth is, they have iron cores. And with Mars, we believe that Mars may be our future. And the reason why we say that is because one of the things that makes the Earth dynamo so unique is that it's like an iron slushy. We believe that with our iron core is actually at that melting, freezing stage, where part of it is solid, part of it is frozen, and part of it is still hot, being heated from the radioactivity inside the Earth's core. And so that's keeping it warm and keeping it melted. But as Earth cools down, that slushy will eventually solidify. It will eventually turn to frozen iron, solid iron. And until that happens, we're going to have a great magnetic shield, because all the processes of the dynamo that we believe are occurring that cause that, it's all part and parcel of this liquid to solid kind of movement. It creates currents inside. It creates motion and convection inside the actual core itself. But once that core is solid, well, there's not going to be any more convection, and we believe the dynamo will cease at that point. And we believe that's what has happened to Mars, and why Mars has a remnant magnetic field. In other words, its rocks remember that it used to have a magnetic shield, but Mars itself anymore doesn't. And so as we sound the interior of Mars and we learn more about its core, it's going to reveal secrets about our future as well as about our past. So that's one of the really cool things, and one of the neat space weather aspects of the Mars InSight lander. And it's also one of the areas where heliophysics and planetary physics collide with space weather, because obviously magnetic shields are very important for keeping us safe. And when you don't have them, you know, the Martian colonists are going to have a lot more hellacious space weather than we do on Earth. And that's, again, for another mini course later. But we can go into all the cool things about that and all the problems that we're going to need to solve. But this is all part of that. By being able to learn more about this core, we'll be able to learn more not only about the Martian history, but also about our own future. So anyway, so now questions. I will, let me see if any of you are still with me after this very long Q&A or mini course. How come all my courses end up being hour and 49 minutes? My goodness, that's a long time. Okay, so let me first go to Patreon and see if anyone's asked me questions on Patreon. And hopefully it will reload. See if I have anybody asking me questions. Oh my gosh, I think so. Hang on. Comments. Hi. Okay. So I'm gonna do Patreon comments first. And hi, Andy. If it's gonna, are you gonna? Come on, load more comments. Oh my gosh. Okay, lots. Okay, who is the target group of this one? Personally, I'm not an aurora chaser, but an amateur radio operator interested in ionosphere reflective radio wave reflection. This is critical for you. This whole, let me go back to a really cool plot. Let me go back to, hold on. To go way back, huh? Boy, I create a lot of charts for you guys. I'm glad you have long, this one. I'm glad you have long, attention spans, because these are long lectures. And I can shorten them up if anybody gets upset at me. Please tell me. I just get so into these topics and I just want to be comprehensive. So I end up taking a lot longer than I should. But so yes, this is extremely important for amateur radio operators, because it lets you know with these different indices, it lets you know when you need to be worried. You know, when can I use auroral propagation? And how come I could use auroral propagation a moment ago, but now I can't? And if I have auroral propagation is working, it's not working so well at the really high latitudes, but it's working. But maybe if I tilt my antenna just at a little bit lower latitude, I'll get something off of aurora, because the KP index is doing really well, or the K index, the local magnetometers in my area are doing really well, but the ones at higher latitudes aren't. If you look at the way these current systems can map back into latitudes on the Earth, it can actually help you. If you're getting a disturbance, a disruption, I know VHF, I've had VHF tower antenna operators tell me, we always get noise during aurora. And someone is just an operator and he's got an antenna that he can actually bend or move or change. And if he knows where that aurora is happening, maybe he can tune his antenna or turn it in such a way that it's not aimed quite in that direction. Or let's say let's say the K indices aren't really going crazy, but the AE is going nuts. Well, that means really, really high latitude stuff going on. And if you can't get propagation, normal propagation, maybe if you tune way up to 80 degrees latitude, northern latitude or southern latitude, then you could actually bounce something off the aurora that you couldn't get otherwise. But looking at the indices first, before just having to climb up on your roof or your tower and go, man, is that it? No, can you hear me now? Can you hear me now? Can you hear me now? I mean, it will help guide you. Now, granted, it's not perfect, but yes, you don't have to be an aurora chaser. These types of indices can help you maybe find the lane in which propagation is actually working and where it's not, even during solar storms. And it can help guide you before you have to go and make big changes to your rig or hang it up for the day, because it gives you at least some indication as to what is possible and what is not. But you have to know where to look. That's the thing, and what to look at. Okay, good. Ann, I hope you get your license. Maybe we'll both get on the bands at the same time, because I'm still not on the band yet, even though I have my license. You can participate here on Patreon or on YouTube. I'm going to go back to YouTube in just a moment and check the feed there, so that's not a problem. Let's see. Okay, how far out is the ring current? It's about the same as, and I'm no ring current expert, but it's about the same as the radiation belts. So it can go out, not quite out to geo. And I may be wrong. Please, Colby, Lemon, or any of you guys out there who are major ring current experts, anybody from Rice, I know you guys know so much more about the ring current. If I mess it up, I'm so sorry. But I do believe it goes out to, it's reasonably co-located with the radiation belt. So that means that it's just inside geosynchronous is the outer edge. But I know there are plumes and things that come out. I do also know that it's actually very active much further in than that. There's a lot of really cool science and physics that happens that we're just beginning to correlate with things that are going on with the ionosphere. Things like plumes and tails and stuff like this, where we're seeing things that are interacting with the plasma sheet and the plasma pause and the plasma sphere that are really cool stuff. And that's really that's like down at L of 1 and 2 is where we're seeing some of these things as far in as that. So, and what does that mean? Oh God, low Earth orbit, really low Earth orbit. So, maybe like 1,200 kilometers or so above the Earth, maybe a little bit more than that. So the ring current can go way out, but the strength of it is much further in than a lot of these the sources of a lot of these others. A lot of the stuff really comes from the tail, which can be 30 plus Earth radii. So basically the radius of the Earth, which is over 6,000 kilometers, almost 6,400, can go all the way down the tail, and so 30 times that, and that's where you get some of these injections. So they map to really, really, really high latitudes. So yeah, there's all sorts of stuff that goes on. Okay. Oh, I'm sorry. Yeah, my voice. Oh, I put my mic on the wrong side again. I'm so sorry, guys. I'm so used to putting my mic on this side when I do my forecasts. I needed to put it on this side. I apologize. Still 5x9 though. Okay, so good. So that was it for the Patreon thing. So I'll go back to YouTube. Okay, let's see. Not sure how I've wound up from Patreon to YouTube. Okay, well, no worries. I'm on YouTube right now, and I'll keep looking. Let's see. I read that there were times the Earth's magnetic poles reverse 4 times in a million years, so there's no set rules. Yeah. No, I don't have any explanation for why that happens, because even though I've got a degree in geophysics, I am not specifically a geophysicist. That is not my discipline, my specialty. I've gotten the rudimentary training required for my field, but my specialty is not the Earth's core. It's not any of that. I'm not a rock person from that point of view. Mine is more space weather and plasma, and more particularly the sun and the events that come off it. So I apologize. I don't have a lot of experience when it comes to geomagnetism and the types of reversals we've seen and why we see them the way they do. UCLA, though, has a lot of really good experts on the Earth's core, and they've got a lot of dynamo experts there. So I might check in with them, because I haven't checked in with them for quite some time, and see if I can learn a little bit more about all that for you. Okay, now, Mars is way too dangerous yet. We're just not prepared, probes and droids, for a couple decades at least. That, and here's the other issue regarding Mars, is that, and I think I talked about this a couple mini courses ago, just getting to Mars is going to be incredibly difficult. Not difficult in the logistic sense, but difficult because we want to send astronauts when we have that window where Mars is at its closest approach, and it's the shortest distance, the shortest time to get to Mars, so we don't have to expose our astronauts to the radiation environment for very long. The sad part about that, though, is that we've had such, the solar activity recently has been so low, and we're seeing cosmic ray penetration like we've never seen. And in 2032, I think it was in the next window, we'd still expect to have reasonably low solar activity cycles. Matter of fact, I think we might even be near solar minimum at that time, which means cosmic rays are just going to be bombarding the spacecraft. So in a sense, it's like the worst time in space, in solar climatology, to go, because the sun is really at a really weak level, and the weaker the sun's shield is, I'm at questions. The weaker the sun's shield is, the more cosmic rays can penetrate. So I don't know. I really don't know if we're gonna be able to send people to Mars. I think we're gonna be stupid and do it. Because it's a once in a lifetime event, and perhaps if Neil deGrasse Tyson really wants to go, maybe he needs to be educated on all the issues, and just send him if he really wants to go, and he can report back. And I feel badly, but I just almost feel like we're asking people to take on too much health-wise to send them now. But it is what it is. Okay, let's see. Any other questions? When it comes to using the indices to forecast substorms, would you recommend using the AE graph over the local magnetometers, or should you use both to complement each other? If you have a local magnetometer nearby, like in your local area, absolutely use it. Those are some of the best, and the more you watch it, the more you get a feel for what the what the types of disturbances are that you should be looking for and what correlates to aurora. It's great to watch them in real time, so when you see aurora, you can say, "Oh, okay, yeah, I watched it just a few moments ago. The perturbation got really strong, and okay, it took about 3 minutes, but here I'm seeing the aurora, really, really brighten." Or vice versa, the aurora seems to lead this kind of thing. You can learn a lot by just trial and error, and if you can have a real time, monitor of it, then you're in great shape. But never neglect the AE indices, because it's over a large set of longitudes, over a lot of set of local times, and it really can tell you a lot of stuff that perhaps a local index can't. Especially if the aurora isn't reached you yet, but you see it's becoming active, and before saying, writing off a storm because it's not going to be strong enough, check the AE index, because maybe the aurora just hasn't rotated to you yet, and yet you see it in the AE index. I'm like, oh, okay, well, maybe I should hang out. So I say the more you use, the better off you are. Just what you use, it's a matter of using it wisely. And hopefully this mini course has helped you understand a little bit more how to use these things wisely. Okay, let's see. Thanks for the feedback. Paul has NOAA running KP better radio backout alerts for hams. Paul oh, okay, thanks for the feedback. Has NOAA running KP better radio backout alerts? I'm not sure I understand that. 200 charts and indexes. Please rewrite that question. I don't understand it as is. What is your take on the Valentina's recent November presentation on the dynamo? Oh, that is, and I'm trying to remember, I think we were talking about a paper of hers where she's done like a lot of statistical analysis, if I recall. And do I believe that we're going into a Dalton-like, or are we in a Dalton-like minimum, and we're going to continue to have activity cycles that are low over the next maybe 2 cycles or so? Yeah, I do. I think that there's a very good chance of that. I think we need to pay attention. I think we'll really have a much better feel for it as this new cycle starts and when it starts. If it starts early, because we've had a lot of spotless days, and there's other indicators. Those are indicators that are saying that the cycle should start early. But there are other indicators that are showing it's still going to be a weak cycle. So I think the heads are still scratching a little bit. I'll be definitely interested to see what goes on at the Space Weather Week in April. I don't know if I'm going to be able to go to that, but that's when we're going to have a lot of solar physicists together looking at all the different models and making the official predictions, hopefully making the official predictions for the next cycle. But I think as we get to the rise of the next cycle, I think that's going to be very telling. I think right now we're pretty much in a hurry up and wait mode, because there are people who, of course, there's 3 sets of people. There are people who think that the cycle is dying out and that we're going to go into a Maunder minimum and sunspots are going to be, a figment of our imagination for the next 100 years. And then there are people, which we know is not true, because we've already seen sunspots for the next cycle, and we've seen the currents for the next cycle. But after that, is it going to continue to weaken and then possibly go into a Maunder minimum? I don't know that. There are some people who are saying that this activity is so dramatic that we're going to pop out of this and it's just going to be a one-shot deal, and we're actually going to have a cycle that's pretty strong, maybe even stronger than the one we had. Not a super strong cycle, but at least stronger than cycle 24. And then there's people like me who are like, I don't think we have enough information yet to know. The problem is that the time scale of solar activity is so slow relative to the human timeline that we have statistics of 1. What kind of prediction can you make with a statistic of 1? We've seen this one other time in history. Really? Are we going to make a prediction based on that? So we can do statistical analyses all we want and manipulate the numbers, and I just don't have any confidence in anything that's being presented. Not to say that she doesn't do fantastic work. I think is it a she? God, I hope so. I'm sorry if it's not. But Zakharova has done amazing work, and it's very understandable and very, very savvy. But the problem is, just like anything in science, when you're dealing with stuff that you're dealing with the frontier of science and things have not been seen, Oftentimes there are variables that you just don't understand and that you can't account for because they've never been observed. So we could very easily fall back into something very different than what has been presented. So I just don't have confidence in anything yet. I do think we need to wait to the rise of the next cycle, and then we'll have a better idea. I don't think we have to wait to solar max, but I think at least to see how things are going. Send Neil to Mars. Yeah, I know. Kind of sad story that came out. I hope it's not true. I'm not going to talk about it, but I just hope it's not true. Science doesn't need another kick in the teeth, especially space science. Okay. Let's see. Thank you so much. Do you see any large CME coming soon? No, not at all. No, there aren't any solar storms being launched at all right now. I'm going back. I'll look in the beginning, or look at the most recent ones soon here. Question, where would you consider the best place to live in the United States with all going on with the sun? Yeah, no, I would think terrestrial weather still trumps solar, space weather when it comes to where I would want to live. That's funny. I haven't really thought of that question before. If space weather were the only factor, where would I live? Honestly, space weather were the only factor, where would I live? Jupiter. I mean, at least in terms of beauty, I can't imagine what it would be like to be able to look at a sky that's got influence from its moons, not only having aurora all over it, but then looking out and seeing all these moons, and all these moons have their own aurora. Could you imagine if our moon had an aurora? What would that look like? If our moon had an atmosphere and a magnetic field, we would see aurora on our moon. So even if you couldn't see aurora directly, let's say you live in Tahiti or something, you could look up at the moon and see aurora, especially if the moon were like a fingernail, like near a new moon where it's almost dark, or even if it were completely dark, you could still see the aurora, maybe even better. And I just would think that would be unbelievable. And the aurora would be connected to the Earth's magnetic field as the moon cuts through the Earth's magnetotail. It would just be an absolutely gorgeous ballet, and our already complicated system would be even more complicated and beautiful because of all the connections and coupling between the moon's magnetic field and our own. We'd have a lot more activity in a lot wilder places. The shadow of the moon across the Earth would have new implications. So, I would love to live in a planetary system that had moons that had aurora, because I think it would just make the night sky that much more just mind-boggling and fascinating and awe-inspiring, to be truthful. So I know that didn't answer your question, but it answered it for me. So okay, so you can't trust a climatologist these days. Yeah, it's hard. I've said this before. Climate science is hard, and I am so grateful I am not a climate scientist. Let's see. Do you have any prediction for the next 3 weeks? Yes, it's going to be quiet. We have a storm right now, and I don't know how it's ramping up. I don't think we're at storm levels. We may reach active levels over the next day or so. Probably won't reach storm conditions. It doesn't look like it's going to be that strong, unfortunately. This hole is, the coronal hole that we're dealing with right now is dying out. It's closing, and so we're losing. The fast wind that's hitting us is not as strong. And then after, the next day or so, it's going to die out, and we'll get maybe up to unsettled to another chance at active conditions in about another week from another kind of remnant coronal hole. And then after that, it's a 2-week wait of nothing. The sun is just not launching anything right now. It's a very, very quiet time, so don't worry about it. Okay, I want to go down here at the very end and see if anyone else has asked questions. And if I've missed your question, I apologize. Does the moon shield us from strong solar storm in some way? No. No, it doesn't. The moon, I'm not even sure that there really is all that much of an influence during solar storms with the moon. I suppose momentarily it could, but the thing is that our Earth's magnetic shield sticks out so far. This little magnetic field that we read with the compass just extends into space so far out that the moon is almost like it's like a needle in a haystack. It just covers a tiny portion of this big magnetic shield. So, it's like a mosquito bite. It protects us from, a tiny little section, and yet the rest of the energy of the solar wind and whatever the sun throws at us, it hits us. So, if you were in a rainstorm, it'd be like having an umbrella the size of, I don't know, a pea, and putting a little pea over your head saying, am I drier? I think that's really what we're dealing with. Now, if the moon had a magnetic field, it may be a little bit bigger. Maybe it'd be a grape. I could put a grape over my head. I have a little grape here. So about that much protection. But as it is, I mean, it's really essentially nothing. So no, I don't think that it affects, it protects us at all. And that's a neat idea, though. See, I love questions like that because it really gets me to think out of the box and stretches my thought concepts. Okay, so thank you for that question. That was fantastic. Let's see, I wrote a personal space weather phone app. What do you think is worth to make it public? There's a lot of apps out there. I have not bothered to make apps. If you guys want to include my forecasts right off of YouTube in your app, feel free. I think I really appreciate when you do that. Apps to me are very scary because you have to keep them up, and until they perfect the browser-based apps where you don't necessarily have to keep up the code because the browser will do it for you. Updating apps all the time is very painful, and if suddenly you have the Space Weather Prediction Center decide to revamp their page and all their links go off and change, it can be very painful. So if you are very dedicated, I think it's worth doing. I think you'd learn a lot about space weather if you do it. But keeping it up is very difficult because, again, we do not have an established operational space weather broadcasting service for the public yet. We have it NOAA and SWPC, is like the National Weather Service. They do it for government agencies. They don't do it for the public necessarily. That's what AccuWeather is for. So we need a space AccuWeather. Once we do something like that, then we'll be good. But till then, apps are going to be a little bit tough to maintain. But by all means, everybody who needs to, the more we have that can spread the news about space weather and what are actionable forecasts, the better off we all are. So, okay, let's see. Thank you for an honest answer. Agenda-free, yeah. If Zarkova is listening, I mean no disrespect. Scientists, the job we do as scientists, especially research scientists, is extremely hard. You put your creative mind to rational concepts and really try to be very rigorous in your analyses. And heck, you're wrong sometimes. But you gave it your best shot, and the cool thing is that when you're wrong, you turn around and it oftentimes gives you insight as to what you can do in the future to see if you're going to be right in a different way. If you may have 5 questions and you try to answer each one systematically, and if you're wrong on the first one, well, hey, at least that one's down. You got these other 4 over here, and that is just part of the nature of science. So I mean. The criticism and the lack of confidence I have is not a lack of confidence in Zarkova itself, but rather the lack in the confidence of our communal understanding of how the sun works and what it's going to throw at us. There are all sorts of aspects to it that are just beginning to be understood and even being considered. Just like I showed you with this talk today, we are still considering new indices. We've seen so many different ways we've done them wrong. And yet we still use them because now to change them, well, you'd have to just start a new index. And so that's what we do. So, that's just the way it is in science. Everything is incremental. And you always learn as much from your mistakes as you do from your successes. So anytime you see a scientist and they put out something, rightly or wrongly, they're doing good. They're making their way through this, and they're helping the world understand a very difficult subject. So I commend Zarkova for their efforts, irrespective of whether I have confidence in our ability to make such estimations right now. Okay. Let's see, middle school books that can be used in middle school. Yes, and I don't have the links with me right now, and I don't have, if you look for Dolores Knipp, search on her, she's got, Dr. Dolores Knipp has got, and that's Knipp, she's got a whole host of middle school books that will be useful. that are written at that level, and I will eventually find those again and post them. I have them on Patreon. They will be posted on Patreon during this behind the scenes thing that I'm doing from the AMS, because Dolores actually talked about them at the 2016 AMS. So if you go to the 2016 AMS website, you will find Dolores Knipp's talk, and you can grab her charts, and in the very last page of her charts, it shows the links for those books, and that's the best I can do right now. But yes, I will eventually have the links like that up on my own website. Okay, so great, thank you. Does leaving dust cloud on the galaxy going to have any effect on the sun? Does leaving the dust cloud of the galaxy? What do you mean? Leaving the dust cloud of the galaxy? I don't really know. The interstellar dust is there all the time. And the heliosphere is the sun's solar wind, the influence of the solar wind. The solar wind blows out to a certain extent, and when it meets, when it doesn't have enough pressure anymore to be felt, it's like if you blow, on your hand, you can feel that out to a certain point, and then at some point you don't feel it anymore. When you lose that feeling, that's essentially the same thing with the solar wind blowing out, and you get to the edge of the heliosphere. And at that point, you don't stand off the dust or any of the other stuff, the magnetic fields or anything else, from the solar system. So does the dust cloud affect the sun? Yes and no. It affects the heliosphere more at the edges, I think, than all of this stuff coming in. Mostly everything out there is charged. I don't think there's many neutrals other than neutrons that are out there. So everything senses the magnetic fields out there. And so, yeah, everything is kind of, it's all connected. So I think we've got a nice magnetic shield around our solar system that protects us from a lot of that stuff. It even protects us from cosmic rays. So, some of them still penetrate, and some of that interstellar dust also penetrates. But it's not any worse than it's ever been. So I don't think that's a problem. Okay, yes, Dolores Knipp, 2016, perfect, yes. Yes, and Dolores is the one, she's a co-panel, or a co-leader on the AMS ad hoc committee with me to do the AMS certification process. We're trying to create a space weather certification for the AMS, and we're at the very early stages of that. But she was one of my she was my co-lead on that panel that I had back at the AMS to kind of talk about this. And she also is the one who put out the space weather article. She's an editor of the Space Weather Journal, by the way. And she put out an article in Space Weather that talked about the 1972 declassification of the mines that were detonated by a solar storm in 72. That has made a huge splash in the media, which I'm so proud of. But she's the author of that. So just in case you feel like you might have recognized her name, that's why. So, okay, guys, I am out of print and very pricey. Yeah, the textbooks are pricey, but there are others. There are others that aren't. Okay, let's see. You guys have got to subscribe to her on Patreon. Oh, that's sweet. So much more detailed info there, worth a few dollars. Oh, that's so sweet. Thank you. That is so sweet. I don't know how to. It says it's held for review, but that's a great message. Thank you so much. Who wrote that? Joseph Roth. Thank you so much. Yeah, there's a lot of stuff I put on Patreon, and some of you guys, all you have to do, I hate to say this, maybe I shouldn't say this, but I will. All you have to do is follow me on Patreon. Just follow me, and there's a lot of posts that I put up that are for patrons only, that are not necessarily pay. You don't even have to pay $1, but I mean, $1 a month. Yeah, there's a lot of stuff that you get on Patreon, and the reason why I put it on Patreon is because I can't do it on Twitter. I don't do well answering comments on YouTube because there's so many trolls, and Patreon is a site that really allows me to go into depth on this stuff without worrying about people being jerks, right? And I know the people that are on Patreon, they really want to know. And I can get into incredibly in-depth dialogues with people on Patreon. And I do. And it's just wonderful. So again, thank you to the Patreon community. You guys are fantastic. And yes, I will keep putting up new stuff, keep asking questions. I will answer this stuff in length. And I love you all so very much. So thank you again, and I hope you had a great time with this mini course. Okay, talk to you soon. Okay, bye.